Hello there, and welcome to Midnight Sleep Science. Tonight, you will journey back to a time when the Earth became something almost unrecognizable, a frozen sphere suspended in space, wrapped entirely in ice. This was not a myth, not a dream, but a real chapter in our planet's history, occurring more than 700 million years ago during a period scientists call the Cryogenian. For tens of millions of years, glaciers stretched from the poles all the way to the equator, and temperatures plummeted to around -50 degrees Celsius. The oceans may have frozen over, sunlight reflected off brilliant white surfaces, and the world became still. Yet this was not the end of Earth's story. It was, in many ways, a beginning. Life, fragile, persistent, and endlessly adaptive, found ways to endure. And when the ice finally melted, it left behind a world transformed, ready to burst into complex forms we would one day recognize as our ancestors. Tonight, you will explore how this frozen world came to be, how life survived against all odds, and how Snowball Earth may have paved the way for the explosion of diversity that followed. So settle in, breathe deeply, and let your mind drift back through deep time. If you enjoy these gentle journeys, feel free to like and subscribe. But for now, let's begin. You stand in your mind more than 750 million years ago on the shores of a world almost unrecognizable. The air around you is thin, carrying only a fraction of the oxygen that fills your lungs today. Perhaps 1 or 2% of what you're used to breathing. If you were truly here, you would struggle with every breath. But the organisms that inhabit this ancient world have never known anything different. They thrive in conditions that would suffocate you, invisible architects building the foundation for everything that comes after. The supercontinent Rodinia stretches before you, a massive landmass that assembled more than 1 billion years ago from the fragments of an even older supercontinent called Columbia. For hundreds of millions of years, Rodinia has dominated the planet's geography, holding together as Earth's interior forces churn beneath it. Mountain ranges rise along ancient collision zones where continents merged, remnants of orogenies, mountain-building events that occurred between 1.3 billion and 1 billion years ago. The Grenville orogeny, one of the most prominent, left its mark across what will one day be eastern North America, evidence of tremendous collisions that welded this supercontinent together. The oceans surrounding Rodinia are warm and shallow in many places, teeming with microscopic life you cannot see with your naked eye. These are the rulers of Earth's biosphere, single-celled organisms that have evolved remarkable strategies for survival. Some harness sunlight through photosynthesis, releasing oxygen as a byproduct, while others thrive in the darker depths where oxygen cannot reach. The atmosphere has been slowly changing for billions of years, oxygen levels gradually climbing. As photosynthetic organisms multiply and iron minerals in the oceans finish absorbing the surplus, the world feels stable, locked in a rhythm that has persisted for eons. The sun shines overhead, though it burns about 6% dimmer than it will in your time. Volcanic activity continues along rift zones and subduction zones, releasing gases into the atmosphere, maintaining a delicate balance of greenhouse gases that keeps the planet's temperature relatively warm. Carbon dioxide cycles through the air, the oceans, and the rocks beneath your feet in a planetary dance of chemistry and geology. Beneath the ocean's surface, carbonate minerals precipitate slowly onto the seafloor, locking away carbon in limestone deposits. On land, chemical weathering, the slow breakdown of rock by water and air, consumes atmospheric carbon dioxide, a process that has been regulating Earth's climate for billions of years. Rain falls on exposed rock, dissolving minerals, carrying ions to the sea where they combine with carbon and calcium to form new stone. This weathering acts as Earth's thermostat, preventing runaway greenhouse warming by removing excess carbon dioxide from the air. The continental interior sits relatively high above sea level, and life here is sparse, limited to microbial communities that can withstand the harsh ultraviolet radiation streaming through an ozone layer thinner than the one that will protect future life. But along the coasts and in the shallow seas, life flourishes in ways you would find extraordinary if you could see it magnified before your eyes. Stromatolites rise from the seafloor like strange layered domes and columns, some reaching several feet high. These structures are not alive in the way you think of life. They are the accumulated remains of countless generations of cyanobacteria, photosynthetic microbes that build mats layer upon layer, trapping sediment and precipitating calcium carbonate as they grow toward the sunlight. During the Proterozoic Eon, which encompasses this time, stromatolites are abundant across Earth's shallow marine environments, testament to the success of these simple but resilient organisms. The cyanobacteria within the stromatolites are ancient engineers, descendants of lineages that have existed for more than 1 billion years. They perform photosynthesis, splitting water molecules and releasing oxygen into the water and atmosphere, a process that has been slowly transforming Earth's chemistry for eons. In fact, cyanobacteria are largely responsible for the oxygenation of Earth's atmosphere, a transformation that began roughly 4 billion years ago during the Great Oxidation Event and continued through the Proterozoic. But oxygen levels in the atmosphere are still far lower than they will be in the future. Most of Earth's ocean depths remain anoxic, devoid of oxygen, and, in some regions, especially in deeper waters and restricted basins, conditions are euxinic. Euxinic waters are both anoxic and sulfidic, containing dissolved hydrogen sulfide produced by sulfate-reducing bacteria that thrive where oxygen cannot penetrate. These bacteria use sulfate ions from seawater to break down organic matter, producing hydrogen sulfide as a toxic byproduct. In the mid-Proterozoic ocean, roughly between 1.8 billion and 800 million years ago, deep ocean conditions fluctuated between ferruginous, rich in dissolved iron, and euxinic states. Recent research suggests that ferruginous conditions may have been more widespread than previously thought, with euxinia developing primarily in coastal regions where organic productivity was high. Trace elements like molybdenum, essential for certain biological processes, would have been scarce in such oceans, potentially limiting the complexity and diversity of life that could evolve. The climate during Rodinia's long existence was generally warm, perhaps even tropical across much of the supercontinent's lower latitudes. Carbon dioxide levels in the atmosphere were likely higher than they are today, maintaining greenhouse warmth despite the fainter sun. Seasonal rains fell on exposed rock surfaces, initiating chemical reactions that slowly consumed carbon dioxide and delivered weathering products to the oceans. This weathering process acted as a planetary thermostat, maintaining equilibrium between volcanic outgassing, which added carbon dioxide to the atmosphere, and chemical weathering, which removed it. Yet equilibrium is not permanence. Deep beneath Rodinia's surface, convection currents in Earth's mantle have been exerting upward pressure, creating zones of weakness in the continental crust. Around 800 million years ago, perhaps earlier, these forces began to pull the supercontinent apart. The rifting would be slow at first, measured in millimeters per year, but over millions of years, it would reshape the planet's surface entirely. The breakup of Rodinia would set in motion a chain of events that would push Earth's climate system past a critical threshold. Volcanic eruptions have been occurring across Rodinia for hundreds of millions of years. But around 825 to 800 million years ago, something shifts. Deep mantle plumes, massive upwellings of hot rock from Earth's interior begin to rise beneath the supercontinent, initiating processes that will fundamentally reshape the planet. These plumes push upward against the continental crust, causing it to arch and stretch. Magma forces its way into cracks, forming dikes of basalt that cut through older rock formations. In what will one day become North America, a massive rift system begins to develop around 1.1 billion years ago, the Keweenawan Rift, also known as the Mid-Continent Rift. This ancient scar extends from present-day Michigan through the Lake Superior region and southward toward Kansas. Though the rift ultimately fails to split the continent completely, it serves as evidence of the immense tectonic forces at work beneath Rodinea's surface. Similar rift systems begin forming across other parts of the supercontinent, in South Australia, South China, Tarim, Kalahari, India, and the Arabian-Nubian Craton. The rifting accelerates between 800 and 750 million years ago as the supercontinent begins to pull apart in earnest. Some researchers suggest that the collision of the Congo Craton with Rodinia around 800 million years ago provided the impetus that broke the supercontinent in two. Regardless of the precise trigger, by 750 million years ago, Rodinia is actively fragmenting. Continental pieces begin to drift apart, creating new ocean basins between them. As Rodinia breaks apart, something crucial happens to Earth's climate system. The fragmentation creates vastly more coastline, new continental margins exposed to the ocean and atmosphere. Fresh rock surfaces, rich in minerals like calcium and magnesium silicates, are exposed to chemical weathering at an unprecedented scale. When rainwater falls on these rocks, it becomes slightly acidic by absorbing carbon dioxide from the atmosphere, forming carbonic acid. This weak acid slowly dissolves the minerals, consuming atmospheric carbon dioxide in the process. Under normal circumstances, this weathering process provides a stabilizing feedback for Earth's climate. If the planet warms, weathering accelerates, consuming more carbon dioxide and cooling the planet. If it cools, weathering slows, allowing volcanic carbon dioxide to accumulate and warm the planet again. But the breakup of Rodinia creates an unusual situation. The continental fragments are positioned primarily at low latitudes near the equator, where temperatures remain warm and rainfall is abundant even as the planet begins to cool. This means that weathering continues at high rates, even as Earth's temperature drops. Carbon dioxide is continuously stripped from the atmosphere, but the cooling doesn't slow the weathering process enough to restore balance. The moderating negative feedback that normally stabilizes Earth's climate becomes less effective. Ice begins to form at higher latitudes, reflecting more sunlight back into space, further cooling the planet. Around this same time, between roughly 800 and 635 million years ago, Earth's atmosphere undergoes another significant change. Oxygen levels, which had been relatively low and stable through much of the Proterozoic, begin to rise during what scientists call the Neoproterozoic oxygenation event. This increase in atmospheric oxygen may be linked to the evolution of early sponges, simple filter-feeding organisms that remove organic matter from seawater, allowing oxygen to accumulate rather than being consumed by decomposition. The rising oxygen has an unintended consequence. Methane, a potent greenhouse gas that had helped keep Earth warm despite the fainter sun, reacts with the oxygen and oxidizes into carbon dioxide, a much weaker greenhouse gas. The atmosphere's ability to trap heat diminishes, the planet cools further, and the ice continues to advance. You cannot see these changes in a single lifetime, or even in 1,000 lifetimes. They unfold across millions of years, shifts so gradual that no single organism would notice them. But they are happening, irreversible and profound, pushing Earth's climate system toward a threshold from which there may be no return. The stage is set. The world stands balanced on the edge of transformation. You are witnessing continental drift in the slowest of motions. measured not in hours or days, but in millions of years. Around 800 million years ago, the forces that had been building beneath Rodinea's crust began to tear the supercontinent apart in earnest. What began as subtle uplifting and volcanic intrusions now transforms into active rifting. The literal splitting of continental crust as Earth's mantle pushes upward with relentless, patient force. The process is not sudden. No single earthquake marks the moment Rodinia breaks. Instead, over tens of millions of years, the continental crust stretches and thins like taffy pulled slowly apart. Fault lines develop, long fractures where blocks of rock slide past one another. Magma from the mantle below rises into these fractures, creating dikes of dark basalt that cut through the older continental rock. In some places, volcanic eruptions send lava flowing across the landscape, building flood basalt provinces that cover thousands of square kilometers. The rift valleys that form resemble, in some ways, the East African rift of your own time, long, linear depressions bounded by parallel fault scarps where the continent is being pulled apart. But the Neoproterozoic rifting is occurring on a grander scale, affecting multiple regions of the supercontinent simultaneously. The Arabian-Nubian shield begins to separate from the Congo Craton. The South Australian margin starts to pull away. The Tarim Block, which will one day be part of Western China, begins its own independent drift. By 750 million years ago, Rodinia has fractured into several distinct continental fragments. Some geologists refer to this configuration as the Greater Gondwana Assembly, though the precise arrangement remains a subject of scientific debate. What is clear from the geological record is that new ocean basins are opening between the separating land masses. Seawater floods into the widening rifts, creating narrow seas that will gradually expand into broader oceans. Over the coming tens of millions of years, the fragmentation of Rodinia has a profound effect on Earth's geography that extends far beyond simply rearranging landmasses. When continents are assembled into a supercontinent, their total coastline length is relatively short. Most of the continental interior sits far from the ocean's influence. But as Rodinia breaks apart, the total length of coastline increases dramatically. Each new rift creates two new continental margins. Shallow seas flood onto the edges of the separating continents, creating vast expanses of shallow marine environments. This increase in coastline and shallow marine environments has critical implications for Earth's carbon cycle. Along these new margins, fresh rock is exposed to chemical weathering at unprecedented scales. Rain falls on newly exposed basaltic rocks, volcanic rocks rich in calcium and magnesium silicate minerals. The rainwater, made slightly acidic by dissolved carbon dioxide from the atmosphere, reacts with these minerals in a process called silicate weathering. The chemical reactions are straightforward but consequential. Carbon dioxide from the atmosphere dissolves in rainwater, forming carbonic acid. This weak acid attacks the silicate minerals in the rock, breaking them down and releasing calcium and magnesium ions into solution. These ions are carried by rivers to the ocean, where they eventually combine with dissolved carbon to form calcium carbonate and magnesium carbonate, limestone and related carbonate minerals that precipitate onto the seafloor. Through this process, carbon is transferred from the atmosphere to solid rock, locked away in carbonate deposits that accumulate on the ocean floor. Under normal circumstances, this silicate weathering process acts as Earth's climate thermostat, providing a stabilizing negative feedback. If Earth warms, evaporation and rainfall increase, accelerating chemical weathering, which removes more carbon dioxide from the atmosphere, cooling the planet. If Earth cools, weathering slows down, allowing volcanic carbon dioxide to accumulate in the atmosphere, warming the planet again. But something unusual is happening during Rodinia's breakup. Many of the continental fragments are positioned at low latitudes, near the equator, where tropical conditions prevail. Even as the planet begins to cool globally, these tropical regions remain warm and wet, sustaining high rates of chemical weathering. The feedback mechanism that normally stabilizes Earth's climate becomes less effective. Weathering continues to strip carbon dioxide from the atmosphere, even as temperatures drop. pushing the climate system toward increasingly cold conditions without the usual compensating response. The dissolution of silicate minerals consumes carbon dioxide at rates that seem modest when measured in the present day. Modern estimates suggest global silicate weathering removes between 0.1 and 0.17 gigatons of carbon per year from the atmosphere. But during periods of intense continental weathering, these rates can increase substantially. When fresh basaltic rock is exposed, as it was during Rodinia's breakup, weathering rates can be 4 to 10 times higher than weathering of older, more chemically stable continental crust. The math becomes stark when you consider the timescales involved. Over millions of years, even modest increases in weathering rates can draw down atmospheric carbon dioxide concentrations dramatically. Computer models suggest that during the late Neoproterozoic, volcanic degassing rates, the rate at which Earth's interior releases carbon dioxide through volcanic eruptions, were anomalously low compared to later periods of Earth history. Measurements of the total length of subduction zones preserved in plate tectonic reconstructions indicate degassing rates roughly doubled between the late Neoproterozoic and the early Phanerozoic, which began around 540 million years ago. This combination, low volcanic outgassing and enhanced weathering, created conditions unlike any that would occur during the following 500 million years of Earth history. Carbon dioxide was being removed from the atmosphere faster than it could be replenished. The planet's greenhouse blanket was thinning. The geological record preserves evidence of these changes in the form of carbon isotope anomalies, shifts in the ratio of carbon-13 to carbon-12 preserved in carbonate rocks. During the Neoproterozoic, carbonate rocks show some of the largest negative carbon isotope excursions in all of Earth history. These excursions represent massive perturbations to the global carbon cycle. Scientists have proposed various mechanisms to explain these isotope anomalies. Some involve the release of methane from seafloor sediments, where it had been stored in ice-like clathrate structures. Methane, when released into the atmosphere, would oxidize to carbon dioxide. But because methane contains mostly the lighter carbon-12 isotope, its oxidation would shift the isotopic composition of atmospheric and oceanic carbon. Other explanations involve changes in the burial rate of organic carbon, shifts in ocean chemistry, or the oxidation of massive reserves of dissolved organic carbon in the oceans. Whatever the precise mechanisms, these isotope excursions tell a story of a carbon cycle in upheaval. The oceans were changing chemically. Oxygen levels in the atmosphere were rising during what scientists call the Neoproterozoic oxygenation event, which likely occurred between roughly 800 and 540 million years ago, with significant increases happening around 635 to 580 million years ago. This increase in oxygen had cascading effects on other atmospheric gases. Methane, a potent greenhouse gas, oxidizes readily in the presence of oxygen. Before the Neoproterozoic oxygenation event, methane may have existed in the atmosphere at concentrations high enough to provide significant greenhouse warming, helping to offset the fainter sun. But as oxygen levels rose, methane was oxidized into carbon dioxide and water. Carbon dioxide is also a greenhouse gas, but it is far less potent than methane, molecule for molecule. Methane traps roughly 25 to 30 times more heat than carbon dioxide over century-long timescales. The result was a net loss of greenhouse warming capacity. Even as volcanoes continued to add carbon dioxide to the atmosphere, the enhanced weathering from Rodinia's breakup stripped it away faster than it accumulated. The atmospheric concentration of carbon dioxide declined. Temperatures began to drop. At high latitudes, where sunlight strikes Earth's surface at shallow angles and delivers less heat per unit area, ice begins to form. Snow accumulates on mountaintops and polar landmasses. Glaciers advance. The planet is cooling, degree by degree, century by century, millennium by millennium, and the ice is about to trigger a feedback loop that will prove almost impossible to stop. The geological record from South China reveals that Earth did not plunge suddenly into full glaciation. Instead, the planet experienced multiple cooling episodes in the tens of millions of years leading up to the Sturtian glaciation. Between approximately 815 and 810 million years ago, a cooling period is recorded in sedimentary rocks. Another permanent cooling period occurred between 800 and 770 million years ago, possibly coinciding with a global carbon isotope excursion known as the Bitter Spring Stage. Then, between 750 and 725 million years ago, a series of episodic cooling and warming cycles left their marks in the rocks. Scientists measured these ancient climate fluctuations using the Chemical Index of Alteration, or CIA, preserved in sedimentary rocks. This index reflects the degree of chemical weathering that occurred when the sediments were formed. High CIA values indicate warm, humid conditions with intense chemical weathering, while low CIA values suggest cold, arid climates where rocks weather slowly. The sediments from this pre-glacial period show distinct drops in CIA values, indicating progressively colder conditions. Direct evidence from low-latitude marine environments confirms that shallow seas were already cold. Millions of years before the onset of the main Sturtian glaciation around 717 million years ago. Oxygen isotope ratios preserved in marine sediments indicate that water temperatures had dropped significantly. Regional glaciations began appearing in different parts of the world at slightly different times. Diachronous glaciations that reflected local conditions but pointed toward a global cooling trend. In Africa, glacial deposits from the Kundalungu glaciation formed roughly between 765 and 735 million years ago. In northwestern China, similar evidence of ice appears in the geological record. These regional ice advances serve as warnings, early tremors before the main event. The ice forms first in the polar regions, where winter sunlight strikes the surface at shallow angles, and summer warmth is insufficient to melt the accumulated snow. Glaciers begin to flow from mountainous regions, grinding their way across the landscape and leaving distinctive marks. Striated bedrock surfaces, where embedded rocks in the glacier's base scratch parallel grooves into the underlying stone. These striations, preserved for hundreds of millions of years, point in the direction the ice traveled. As carbon dioxide levels continue to fall and temperatures drop further, sea ice begins forming on the ocean surface at high latitudes during winter months. At first, this ice melts each summer, but as cooling continues, some persists year-round. The white surface of the ice reflects sunlight, far more than the dark ocean water beneath, sending solar energy back into space rather than absorbing it as heat. This is where the feedback begins. Subtle at first, but inexorable in its logic. More ice means more reflected sunlight. More reflected sunlight means cooler temperatures. Cooler temperatures mean more ice. The system is beginning to tip, balanced on the edge of a transition that will transform Earth more dramatically than anything that has happened in its entire 4 billion year history. The continental fragments of former Rodinia drift in their new configurations, unaware that their breaking apart has set forces in motion that will soon encase them all in ice. Shallow tropical seas still support microbial life. Stromatolites still build their layered structures along warm coastlines. But the planet's climate system is shifting beneath these surface continuities, moving toward a state that will test the limits of life's ability to endure. The cooling accelerates, the ice advances, and soon there will be no stopping it. You are watching a transformation that operates on the simplest of physical principles, yet produces consequences so extreme they seem almost impossible. The ice that has begun forming at high latitudes does more than simply cover the land and sea. It fundamentally changes how Earth interacts with incoming sunlight. This change triggers what scientists call the ice albedo feedback, one of the most powerful positive feedback mechanisms in the climate system. Albedo is a measure of reflectivity, expressed as the fraction of incoming sunlight that a surface reflects back into space rather than absorbing as heat. Dark surfaces, like open ocean water or exposed rock, have low albedos, typically between 0.05 and 0.15, meaning they absorb 85 to 95% of the sunlight that strikes them. This absorbed energy warms the surface, radiating heat into the atmosphere and helping to maintain Earth's temperature. Ice and snow have dramatically different properties. Fresh snow can have an albedo as high as 0.8 to 0.9, reflecting 80 to 90% of incoming sunlight back into space. Sea ice typically has an albedo between 0.5 and 0.7. When ice replaces dark ocean water or vegetation-covered land, the amount of solar energy absorbed by Earth's surface drops dramatically. Less absorbed energy means cooler temperatures. Here is where the feedback begins its work. As the planet cools and ice expands, more of Earth's surface becomes highly reflective. More reflected sunlight means less absorbed energy, which leads to further cooling. The cooling allows ice to expand even more, increasing the reflective surface area, which drives additional cooling. The loop feeds on itself, amplifying the initial change. During the early stages of glaciation, this feedback operates gradually. Ice advances from the poles during winter months and retreats somewhat during summer. The boundary between ice-covered and ice-free regions shifts back and forth with the seasons, responding to temperature changes and variations in snowfall and melting. At high latitudes, above roughly 60 degrees north and south, where winter brings months of weak sunlight or darkness, ice can persist year-round once it forms. But as atmospheric carbon dioxide continues to decline due to enhanced weathering from Rodinia's breakup, and as methane oxidizes into the less potent greenhouse gas carbon dioxide, global temperatures drop further. The ice begins to survive summer melting at progressively lower latitudes. Glaciers flowing from mountainous regions reach the sea, carving icebergs that drift into lower latitude waters. Sea ice, which forms when ocean water freezes, begins to cover larger areas of the ocean surface. Climate models that simulate this period reveal how the feedback accelerates. Once ice coverage expands to roughly 30 degrees latitude in both hemispheres, covering about half of Earth's surface, the system approaches a critical threshold. Beyond this point, the ice albedo feedback becomes so strong that it overwhelms the stabilizing mechanisms that normally regulate Earth's climate. The planet enters a runaway glaciation. Around 717 million years ago, this threshold is crossed. The Sturtian glaciation, named after the Sturt Formation in South Australia where evidence was first identified, begins in earnest. Geological evidence suggests that the ice sheet advance at the start of the Sturtian glaciation lasted for less than 1 million years, an astonishingly rapid transition on geological timescales. Within perhaps a few 100,000 years, ice advances from both poles toward the equator. The physics of this advance are straightforward but relentless. Each degree of cooling allows ice to push slightly farther toward the equator. Each expansion of ice coverage increases Earth's albedo, reducing the amount of solar energy absorbed, driving further cooling. The system is locked into a positive feedback loop, with each change amplifying the next. Nothing on the surface can stop it. The weathering of rock that helped trigger the cooling in the first place now diminishes as ice covers the continents. But this change comes too late. The ice albedo feedback has taken control of the climate system. The sea ice that forms on the ocean surface develops through a process distinct from the freezing of fresh water. Seawater must reach approximately 1.8 degrees Celsius, 28.8 degrees Fahrenheit, to freeze, lower than the 0-degree freezing point of fresh water, because dissolved salt lowers the freezing temperature. Furthermore, as seawater cools toward the freezing point, it becomes denser and sinks away from the surface. The top 100 to 150 meters of ocean water must cool to the freezing point before ice can begin forming at the surface. When freezing finally begins, small needle-like ice crystals called frazzle form first. These crystals are typically 3 to 4 millimeters in diameter and consist of nearly pure fresh water, as the freezing process expels salt. In calm waters, frazzle crystals float to the surface and bond together to form a thin, smooth ice called grease ice, named for its resemblance to an oil slick. This grease ice develops into a continuous, thin sheet called nilus, which is initially very thin and dark, becoming lighter as it thickens. Once a stable ice sheet forms, additional growth occurs from beneath as water freezes directly onto the bottom of the existing ice. This bottom growth, called congelation ice, proceeds more slowly than the initial frazzle formation, because the ice acts as an insulator between the cold atmosphere above and the warmer water below. Heat from the ocean must conduct through the ice layer before being released to the atmosphere, and ice growth slows as thickness increases. But despite this slowing, once sea ice covers a significant portion of the ocean's surface, its high albedo, typically between 0.5 and 0.7 for sea ice, compared to just 0.06 to 0.12 for open water, dramatically reduces the amount of solar energy absorbed by the ocean. The reflected sunlight never warms the surface, allowing temperatures to drop further and more ice to form. Climate models reveal how rapidly this feedback can operate once triggered. According to simulations, once glacial ice advances to within 25 to 30 degrees of the equator, the ice albedo feedback causes ice to spread rapidly to the tropics. One modeling study examining an impact-induced cooling scenario showed that once the feedback threshold is crossed, transition to near-global ice coverage can occur in as little as 7 to 9 years. While the actual Sturtian glaciation likely took longer, geological evidence suggests the initial ice advance lasted less than 1 million years. This is still extraordinarily rapid on geological timescales. The feedback operates with particular strength because of the configuration of continents during this period, with Rodinia's fragments positioned primarily at low latitudes. Large expanses of tropical and subtropical ocean remain exposed. When sea ice begins forming on these low-latitude oceans, the contrast between the bright ice and dark water creates a powerful albedo difference. The tropical regions, which receive intense sunlight year-round, now reflect much of that energy back into space rather than absorbing it. The sun during this period is already 6% fainter than it will be in your time, providing less total energy to warm the planet. This dimmer sun makes Earth's climate system more sensitive to changes in albedo. With less incoming solar energy, a smaller decrease in absorbed energy, caused by expanding ice coverage, can trigger a larger temperature drop. Once the ice reaches the equator, the planet enters a state that scientists call hard Snowball Earth. Climate models suggest that sea ice could thicken to depths of 1 kilometer or more in some regions. The entire ocean surface becomes covered, sealing off the exchange of heat and moisture between the ocean and atmosphere. The only energy input comes from sunlight, most of which is now reflected away, and from the planet's internal heat, which continues to escape through volcanic activity, but is insufficient to warm the frozen surface. The ice albedo feedback has done its work. Earth has crossed a threshold from which recovery seems almost impossible. The ice advances toward the equator from both hemispheres, marching relentlessly equatorward as temperatures plummet. Climate models and geological reconstructions suggest that once sea ice reaches approximately 25 to 30 degrees latitude, the remaining transition to complete ice coverage at the equator happens rapidly, perhaps within centuries to millennia, though geological resolution cannot capture such brief intervals. By around 717 million years ago, the ice reaches the tropics. The global mean temperature drops to approximately 50 degrees Celsius, 74 degrees Fahrenheit, colder than anywhere on modern Earth except the interior of Antarctica during its darkest winter months. At the equator itself, temperatures average around 20 degrees Celsius, 10 degrees Fahrenheit. These are temperatures that would seem unimaginable for tropical latitudes, yet oxygen isotope ratios preserved in ancient glacial ice from this period indicate conditions even more extreme. Some estimates based on isotope data suggest temperatures at the equator may have dropped to as low as 40 degrees Celsius, though translating ancient isotope signals into absolute temperatures involves significant uncertainties. The sea ice that covers the ocean grows thick. In tropical regions, where geothermal heat flux from Earth's interior and any remaining heat in the deep ocean must conduct through the ice before escaping to space, the ice reaches thicknesses of approximately 1 kilometer. roughly 1,000 meters. Near the poles, where surface temperatures are coldest and ice has been accumulating longest, thicknesses may exceed this substantially. The ice is not uniform or still. Despite being sealed beneath a kilometer of frozen ocean, the water below remains liquid, warmed by the steady geothermal heat flux from Earth's interior, about 0.1 watts per square meter, modest but persistent. This heat creates temperature gradients within the ocean, driving circulation patterns. Warm water from near the seafloor rises toward the ice-covered surface, while cold, dense water sinks. Surprisingly, the ocean beneath the ice is not stagnant but dynamically mixed, with vigorous circulation patterns including equatorial meridional overturning, zonal jets, and even a well-developed eddy field on land. Glaciers flow from continental interiors toward the coasts, grinding across bedrock and leaving the scratches and grooves that will be preserved for hundreds of millions of years. Seasonal temperature swings are dramatic. Without the moderating influence of liquid oceans, which absorb heat during summer and release it during winter, continental surfaces experience wild fluctuations between summer warmth, if it can be called that, and winter cold. Near the equator, during summer when the sun passes directly overhead, surface temperatures on dark rock surfaces exposed through thin ice or snow may briefly rise above freezing, creating meltwater that refreezes when temperatures drop. The atmosphere is cold and extraordinarily dry, with most of Earth's water locked in ice, and with frigid temperatures that hold very little moisture in the air even when sublimation occurs. The atmosphere contains perhaps 1/10 the water vapor of modern times. Precipitation, when it occurs, falls as snow. In some regions, atmospheric circulation patterns transport this snow from areas where sublimation exceeds deposition to areas where the reverse is true, allowing glacial ice to flow and thicken over geological time. The planet has entered a state without precedent in its earlier history. This is not a typical ice age, like those that will occur in the Pleistocene epoch millions of years in the future, where ice sheets advance and retreat, but tropical regions remain warm and wet. This is something far more extreme, a state that seems almost stable, as though Earth might remain frozen indefinitely. The ice albedo feedback has brought the planet to this frozen equilibrium. But equilibrium, even when it appears permanent, can be disrupted by forces that operate on timescales longer than the freezing itself. You are standing, in your imagination, on a planet that has become unrecognizable. The year is approximately 717 million years ago, and the Sturtian glaciation has begun in earnest. Within less than 1,000,000 years, perhaps only a few 100,000, ice has advanced from both poles to meet at the equator. Earth has transformed into something unprecedented in its long history. A frozen sphere suspended in space, its surface covered almost entirely by ice and snow. From space, if you could observe it, the planet would appear brilliantly white, reflecting most of the sunlight that reaches it back into the darkness. The familiar blue of liquid oceans has vanished beneath a frozen lid. The browns and greens of continents are buried under glacial ice sheets that flow slowly from continental interiors toward the coasts. Only in a few places might dark rock surfaces show through where wind has scoured away snow or where steep slopes prevent ice accumulation. The sun still rises and sets, tracing its familiar path across the sky, but it provides 6% less energy than it will in your distant future. Even the sunlight that does reach the surface accomplishes little warming. Most of it simply reflects away from the bright ice and snow, bouncing back into space without delivering its heat. The ice albedo feedback that initiated this frozen state now maintains it, a self-reinforcing cycle that keeps the planet locked in extreme cold. The oceans, which once moderated Earth's climate by absorbing heat during warm periods and releasing it during cold ones, are sealed beneath ice. At the equator, where tropical waters once teemed with microscopic life, sea ice extends to depths of approximately 1 kilometer, 1,000 meters of frozen ocean. Near the poles, where ice has been accumulating longest and where surface temperatures are coldest, the thickness may be even greater. This sea ice did not form overnight. It accumulated through the same process that forms sea ice today, beginning with the freezing of the ocean's surface layer when temperatures dropped below approximately 1.8 degrees Celsius. Small ice crystals formed and joined together, creating thin sheets that thickened from beneath as more water froze onto the bottom of the ice. Year after year, century after century, millennium after millennium, the ice grew thicker as heat from the ocean below conducted through the ice layer and escaped to the frigid atmosphere above. Beneath this frozen lid, the ocean remains liquid. Heat from Earth's interior, geothermal energy that flows constantly from the planet's core and mantle, warms the deep ocean water from below. This heat flux is modest, only about 0.1 watts per square meter, but it is steady and unceasing. The heat creates temperature differences in the water, driving circulation patterns that keep the deep ocean from freezing solid. These circulation patterns are not gentle. The ocean beneath the ice churns with currents driven by temperature and salinity differences. Warm water rises from depth toward the ice-covered surface, while cold, dense water sinks. Equatorial meridional overturning currents develop, zonal jets form, and even eddies, circular current patterns, appear in the darkness beneath the ice. The ocean is not dead, just isolated from the atmosphere and sunlight above. On the continents, glacial ice sheets cover the landscape. These continental glaciers are distinct from the sea ice covering the oceans. They form from accumulated snowfall on land, which compresses under its own weight into solid ice that flows plastically under pressure. The ice sheets grind slowly across bedrock surfaces, carving grooves and scratches, striations that will be preserved in the rock for hundreds of millions of years, long after the ice has melted. The atmosphere above this frozen world is thin and extraordinarily dry. With most of Earth's water locked in ice, very little moisture circulates through the air. What little water vapor exists comes from sublimation, the direct transformation of ice into vapor without passing through a liquid phase. Clouds are rare and insubstantial. Precipitation, when it falls, comes as fine, dry snow. Global mean temperatures have plummeted to approximately 50 degrees Celsius. At the equator, where the sun still delivers its most direct rays, temperatures average around 20 degrees Celsius, though some estimates based on oxygen isotope data suggest conditions may have been even colder, perhaps as low as 40 degrees Celsius. These are not fleeting conditions that will pass in years or centuries. The Sturtian glaciation, once established around 717 million years ago, will persist for approximately 57 million years, lasting until roughly 660 million years ago. This is not measured in human lifetimes or even in the lifespans of civilizations. This is an interval of time so vast that entire mountain ranges could rise and erode away. Continents could drift thousands of kilometers, and countless generations of whatever microbial life survives could live and die without ever knowing a world that wasn't frozen. The atmosphere continues to circulate, driven by temperature differences between the equator and poles, and by Earth's rotation. Even on a frozen planet, the equator receives more direct sunlight than the poles, creating temperature gradients that drive wind patterns. The atmospheric circulation develops into a relatively simple structure characteristic of what scientists call a dry atmosphere, one with very little water vapor. Hadley cells form near the equator, where air warmed by the sun's rays rises, flows poleward at high altitude, descends in the subtropics, and returns toward the equator near the surface. These circulation cells, though much weaker than those on a modern Earth with liquid oceans and abundant atmospheric moisture, still transport heat from the sunlit equator toward the darker poles. The strength of this circulation varies considerably, depending on subtle details of atmospheric properties, but it exists nonetheless, a ghostly remnant of the vigorous circulation that characterized the pre-glacial world. Seasonal temperature variations persist, and near the equator they can be surprisingly large. On exposed land surfaces, places where wind has scoured away snow or where steep terrain prevents accumulation, the annual temperature swing can exceed 24 degrees Celsius, and in some locations may reach 30 degrees Celsius or more. This is because Earth's orbital eccentricity, the degree to which its orbit around the Sun deviates from a perfect circle, affects how much sunlight reaches different parts of the planet during different seasons. When Earth's orbit is more elliptical and the timing of perihelion, the point when Earth is closest to the Sun, coincides with summer in one hemisphere, that hemisphere experiences dramatically stronger seasonal heating. Near the equator, where the Sun passes directly overhead twice each year, summer temperatures on dark rock surfaces can briefly rise above freezing, even while the global mean temperature remains far below zero. Meltwater forms in puddles on sun-warmed rock, then refreezes when temperatures drop at night or when winter returns. These seasonal cycles create thermal stress in the rocks, expansion when warmed, contraction when cooled, that slowly fractures them. Sand grains work their way into the cracks, forming ice wedges and sand wedges that will be preserved in the geological record as evidence of freeze-thaw cycles even in equatorial regions. These features, discovered in ancient rocks that were once at low latitudes, provide some of the most compelling evidence that Earth truly was frozen from pole to pole. But for most of the planet, for most of the time, the cold is unrelenting. At the poles, winter brings months of darkness, during which no sunlight reaches the surface at all. Summer provides constant daylight, but at such shallow angles that little warming occurs. The ice simply accumulates, millennium after millennium. This is Earth at its coldest extreme, locked in a state that seems as though it might last forever. The planet has become a frozen experiment, testing whether life can endure conditions more severe than any that will be experienced. Again, in the billions of years that remain in Earth's future, the curtailment of photosynthesis across most of Earth's surface represents one of the most profound changes. With ice covering the oceans to depths of a kilometer or more, sunlight cannot penetrate to the liquid water below, where photosynthetic organisms might survive. Even in tropical regions, where seasonal warming might thin the ice somewhat, the depth remains far too great for light to reach through. The microbial communities that once thrived in the ocean's sunlit surface waters, the cyanobacteria and other photosynthetic microbes that dominated Earth's biosphere, are cut off from their energy source. This interruption of photosynthesis has cascading consequences for atmospheric chemistry. Oxygen production, which has been slowly rising during the Neoproterozoic, comes to a near standstill. What oxygen remains in the atmosphere begins to be consumed by chemical weathering of rocks and oxidation of reduced iron and sulfur compounds exposed to the air. Non-oxidized iron-rich rocks, formations that could not form in an oxygen-rich atmosphere, begin to accumulate in certain geological environments, preserved as evidence of the depleted oxygen conditions. Yet Earth's internal processes continue unperturbed by the frozen surface. Deep beneath the ice, volcanoes still erupt. The planet's interior remains hot, heated by the radioactive decay of elements like uranium, thorium, and potassium that were incorporated into Earth when it formed. Magma rises through the crust, breaking through in volcanic eruptions that spew lava, ash, and gases into the frozen world above. These eruptions emit water vapor, carbon dioxide, sulfur dioxide, and other volcanic gases into the atmosphere. Under normal circumstances, the carbon dioxide would be removed by weathering and precipitation, cycled through the ocean, and eventually locked into carbonate rocks on the seafloor. But with most of the continents buried under ice, chemical weathering has nearly ceased. Rain still falls, but sparingly in the cold, dry atmosphere, and it falls mostly as snow. The carbon dioxide released by volcanoes begins to accumulate in the atmosphere unchecked. But this accumulation is slow, painfully slow by any measure except geological time. Volcanic outgassing rates during the Sturtian glaciation were unusually low compared to later periods of Earth history. The total length of mid-ocean ridges, underwater volcanic mountain chains where new oceanic crust forms, was at a minimum during this period. resulting in reduced volcanic carbon dioxide emissions. The accumulation of carbon dioxide will take millions of years before it reaches levels sufficient to break the frozen planet's grip. Meanwhile, on the ice surface, dust accumulates. Volcanic eruptions eject fine ash particles into the atmosphere. Winds erode exposed rock surfaces, creating dust that is carried aloft. This dust settles onto the ice and snow, darkening the surface. Over millions of years, ice dynamics, the slow flow of glacial ice from regions of accumulation to regions of ablation, transport this dust, concentrating it in certain areas. The accumulation is subtle, measured in micrometers per year, but time is abundant. After millions of years, the dust layer thickens, particularly in tropical regions, where ice flow patterns concentrate the accumulated particles. This dust, though sparse, begins to lower the albedo of the ice surface, allowing slightly more sunlight to be absorbed rather than reflected. The planet endures, frozen and nearly silent, locked in a state that seems eternal but is merely long. 57 million years will pass before the Sturtian glaciation ends. In that vast expanse of time, continents will continue their slow drift, carried by the convection currents in Earth's mantle. Volcanoes will erupt countless times, gradually building the atmospheric carbon dioxide that will eventually trigger deglaciation. And somewhere, in refugia we can only guess at, life will persist, waiting for the thaw. You might wonder how scientists can possibly know about events that occurred more than 650 million years ago, before any animals with hard shells existed, before plants colonized the land, before even the earliest fossils of complex multicellular life appeared in the rock record. The answer lies in the rocks themselves, which preserve physical signatures of the frozen world in ways that remain legible across vast spans of geological time. The most striking evidence appears in glacial deposits found at latitudes that were near the equator during the Neoproterozoic. These deposits, called diamictites, are chaotic mixtures of sediment, rocks of all sizes jumbled together without the sorting that normally occurs when water or wind transports particles. Large boulders sit embedded in fine-grained mud, a combination that can only form when ice carries the material. Glaciers and icebergs are indiscriminate transporters, freezing rocks of every size into their mass and dropping them wherever melting occurs. In the Flinders Ranges of South Australia, these glacial deposits from the Sturtian period stretch across the landscape, exposed by millions of years of erosion. The rocks tell a clear story. Ice once covered this region, but South Australia's location during the Neoproterozoic was not at a high latitude where ice might be expected. It was positioned near the equator. This is the crucial detail that transforms local glacial evidence into proof of global ice coverage. Recent discoveries have confirmed similar evidence in other locations that were also at low latitudes during Snowball Earth. In 2024, researchers working on Pikes Peak in Colorado identified ancient rocks containing glacial debris that date to the Cryogenian period. The rocks show signs of having been transported and deposited by ice. And paleomagnetic analysis, the study of ancient magnetic fields preserved in rocks, indicates these deposits, formed at tropical or near tropical latitudes. These paleomagnetic signatures provide some of the most compelling evidence for Snowball Earth. When rocks form, magnetic minerals within them align with Earth's magnetic field, like tiny compass needles pointing toward the poles. This magnetic orientation gets locked into the rock as it solidifies or as sediments compact and harden. By measuring these ancient magnetic orientations and comparing them to Earth's magnetic field geometry, scientists can determine the latitude at which the rocks formed. The mathematics is straightforward. At the equator, Earth's magnetic field runs parallel to the surface, while at the poles it points straight down. Rocks containing glacial deposits that show magnetic inclinations consistent with equatorial or low latitude positions provide powerful evidence that ice reached the tropics. Multiple sites around the world preserve such signatures, forming a consistent global pattern. In Scotland and Ireland, Rocks from the Porterskeg Formation have been confirmed as rare records of Snowball Earth glaciation. These rocks contain the distinctive features of glacial deposits, poorly sorted sediments, dropstones where ice-rafted boulders fell into marine muds, and other signatures of ice presence. The formations represent some of the best preserved records of this ancient glaciation anywhere on Earth. Dropstones themselves tell a vivid story. These are isolated large rocks found within layers of fine-grained sediment deposited in deep water. The only way such rocks can reach the middle of an ocean basin is by being frozen into icebergs that carve from glaciers, float across the sea and eventually melt, dropping their rocky cargo onto the seafloor far from any coast. The presence of dropstones in rocks that formed in tropical ocean basins provides direct evidence of ice floating in equatorial waters. Another distinctive feature preserved in these ancient rocks is the presence of striated pavements, bedrock surfaces scored with parallel scratches. These striations form when glaciers flow across rock surfaces, and stones embedded in the ice base act like sandpaper, carving grooves into the underlying bedrock. The orientation of these scratches reveals the direction of ice flow, allowing scientists to reconstruct ancient ice sheet movements. Perhaps most distinctively, a layer of unusual carbonate rock directly overlies the glacial deposits in many locations worldwide. These cap carbonates, as they are called, form continuous layers of limestone or dolostone that sit sharply on top of the glacial sediments. Their presence is so consistent, appearing above Snowball Earth deposits on multiple continents, that they serve as a marker horizon, a distinctive signature of the deglaciation that ended each frozen episode. The cap carbonates often display unusual features. They contain large ripple marks formed by strong underwater currents, structures that suggest turbulent conditions during deposition. Some show evidence of bacterial activity preserved in their layers. The abrupt juxtaposition of glacial deposits below and carbonate rocks above, with no gradual transition, indicates rapid environmental change. A sudden shift from extreme cold to conditions warm enough for massive carbonate precipitation. You will learn more about these remarkable formations later, but their mere existence provides powerful evidence for both the glaciation and its ending. Another distinctive type of rock associated with Snowball Earth glaciations is banded iron formation. These sedimentary rocks consist of alternating layers of iron-rich and silica-rich material, creating a striped appearance. Banded iron formations were common early in Earth's history, before oxygen became abundant in the atmosphere. But they largely disappeared after the Great Oxidation Event around 2.4 billion years ago. Their reappearance during the Neoproterozoic glaciations is significant. During Snowball Earth, the frozen ocean was entirely cut off from the atmosphere. Without the normal exchange between sea and air, oxygen could not dissolve into the water. Iron from hydrothermal vents on the seafloor, volcanic hot springs that continuously release dissolved metals into the ocean, could accumulate without immediately oxidizing. Normally, atmospheric oxygen oxidizes any dissolved iron almost immediately, preventing banded iron formations from accumulating. But beneath the ice, in an ocean isolated from the air, iron accumulated until conditions changed. The layering within these banded iron formations preserves another remarkable piece of evidence. Detailed analysis of the layers reveals cycles that correspond to Earth's orbital variations, the Milankovitch cycles that affect how much sunlight reaches different parts of the planet during different seasons. These cycles include changes in Earth's axial tilt, the shape of its orbit around the Sun, and the precession of its rotation axis. The presence of nearly all orbital cycles preserved in banded iron formations deposited during the Sturtian glaciation indicates that even beneath the ice, these astronomical influences affected conditions at the seafloor. The global distribution of Neoproterozoic glacial deposits itself tells a story. Glacial sediments from this period appear on nearly every continent, in North America, South America, Africa, Australia, Asia, and Europe. When researchers reconstruct the ancient positions of these continents using paleomagnetic data and other geological evidence, they find that glacial deposits formed at virtually all latitudes, from polar regions to the equator. This global distribution, combined with the low-latitude paleomagnetic signatures, provides some of the strongest evidence that the glaciations were truly worldwide. The Neoproterozoic glaciations also contributed to one of the most significant features of Earth's geological record, the Great Unconformity. This is a widespread gap in the rock record where billions of years of ancient rocks are missing, having been eroded away. Research suggests that glacial erosion during Snowball Earth events removed enormous quantities of rock from continental surfaces, carving away kilometer-scale thicknesses of crust. The erosion was distributed across all continents in proportion to the duration of each glacial interval. The rocks remember. They preserve the evidence in layers and structures that have endured for more than 650 million years. Determining precisely when these glaciations occurred requires sophisticated dating techniques. The most commonly used method for dating ancient rocks is uranium-lead radiometric dating. This technique relies on the fact that uranium atoms naturally decay into lead atoms at a constant, predictable rate. By measuring the ratio of uranium to lead in certain minerals, particularly zircon crystals, which are extremely durable and contain trace amounts of uranium when they form, scientists can calculate when the minerals crystallized. Zircon crystals act as tiny time capsules. When a zircon forms in molten rock, it incorporates uranium into its crystal structure, but excludes lead. As time passes, the uranium gradually decays into lead, and by measuring how much of each element remains, scientists can determine the crystal's age with remarkable precision. For Snowball Earth research, zircons found in volcanic ash layers that were deposited just before, during, or after the glaciations provide crucial age constraints. Recent uranium lead dating, combined with another technique called rhenium-osmium dating, suggests that the Sturtian glaciation began around 717 million years ago and ended approximately 660 million years ago. More precise measurements using hematite, an iron oxide mineral that forms in oxidizing conditions and can also be dated using uranium-lead methods, have refined the timing of specific events within the glaciation. These dates indicate that glacial onset and termination were globally synchronous, meaning the entire planet froze and thawed at essentially the same time. The chemistry preserved in rocks from this period reveals equally compelling evidence. Carbon isotopes, different forms of carbon atoms that have the same chemical properties but different masses, show dramatic variations in Neoproterozoic sediments. During normal times, the ratio of carbon-13 to carbon-12 in carbonate rocks remains relatively stable, reflecting steady-state processes in the global carbon cycle. But during the Neoproterozoic, this ratio swings wildly, reaching some of the most negative values recorded in all of Earth history. These negative carbon isotope excursions, periods when rocks contain unusually high proportions of the lighter carbon-12 isotope, indicate massive disruptions to the carbon cycle. Various explanations have been proposed, including the oxidation of dissolved organic carbon that accumulated in the oceans, the release of methane from seafloor sediments, or changes in the burial rate of organic matter. Whatever their precise cause, these isotope anomalies appear repeatedly in rocks associated with Snowball Earth glaciations, providing a geochemical fingerprint of the extreme conditions. Identifying glacial deposits themselves requires careful analysis. The term tillite refers to lithified till, sediment deposited directly by glacial ice that has been compressed and hardened into rock over millions of years. True tillites display distinctive features. They are poorly sorted, containing particles, of all sizes, from fine clay to boulders, mixed chaotically together. They may contain faceted and striated stones, rocks that were ground against each other or against bedrock, while frozen in moving ice, producing flat surfaces and parallel scratches. However, not all poorly sorted sedimentary rocks are glacial in origin. Mud flows, debris flows, and other mass movement processes can create similar-looking deposits. This is why geologists look for multiple lines of evidence when identifying ancient glacial deposits. The presence of dropstones in deep-water sediments, striated bedrock pavements beneath the deposits, association with other glacial features, and, critically, paleomagnetic evidence indicating low-latitude deposition. The convergence of all these lines of evidence, glacial deposits at low latitudes, distinctive cap carbonates, banded iron formations, carbon isotope anomalies, and precise radiometric dates, builds an overwhelming case for the reality of Snowball Earth. The rocks do not lie, though reading their message requires patience, precision, and the ability to think across timescales that dwarf human experience. You might wonder how life could possibly survive on a planet encased in ice for tens of millions of years. The question is not merely academic. It strikes at the heart of understanding life's resilience and the limits of habitability. With photosynthesis curtailed across most of Earth's surface, with temperatures far below freezing, and with the oceans sealed beneath ice up to a kilometer thick, the conditions seem incompatible with biological existence. Yet the geological and biological evidence tells us unequivocally that life did survive. The survival was not easy, and it likely came at great cost to diversity. The Marinoan glaciation, the second major snowball event that occurred after the Sturtian, appears to have significantly impacted marine biomass and restrained the evolution of early life. Chemical analyses of sediments suggest that biological productivity plummeted during glaciation. The oceans beneath the ice were not teeming with life in the way they had been before the freeze, but some organisms endured, clinging to existence in refugia, isolated pockets where conditions permitted survival. One of the most plausible refugia would have been meltwater ponds on the surface of tropical ice sheets. During summer months at the equator, where the sun still delivered relatively intense radiation, despite the planet's high albedo, dark patches on the ice surface could warm enough to create small pools of liquid water. These cryoconite ponds, as they are called in modern glaciology, form when dust or volcanic ash settles on ice, lowering the albedo locally and allowing sunlight to melt the surrounding ice. Modern analogues exist in Antarctica, where cryoconite ponds support microbial communities despite extreme cold. The ponds are small, often just meters across, and shallow, but they provide liquid water, sunlight, and a refuge from the frozen wasteland around them. During Snowball Earth, similar ponds could have formed on tropical ice sheets during peak summer, when solar radiation was strongest. Photosynthetic microorganisms, cyanobacteria, and other primary producers could have survived in these ponds, producing oxygen and organic matter that supported small, isolated ecosystems. The ponds would have been ephemeral and scattered, freezing solid during winter and reforming the following summer. But this cycle, repeated millions of times over the duration of the glaciation, could have maintained genetic diversity and allowed evolution to continue, albeit at a drastically reduced pace. The organisms living in these refugia would have been subjected to intense selective pressure. Only those capable of withstanding repeated freeze-thaw cycles, high ultraviolet radiation due to the thin atmosphere, and extremely limited nutrients would survive. Another potential refuge lay beneath the ice, near hydrothermal vents on the ocean floor. These volcanic hot springs continuously release heat and chemicals from Earth's interior, creating oases of warmth in the frigid deep ocean. Modern hydrothermal vent communities thrive without sunlight, powered instead by chemosynthesis, metabolic processes that derive energy from chemical reactions rather than photosynthesis. During Snowball Earth, similar communities could have persisted around volcanic vents, feeding on hydrogen sulfide, methane, and other reduced chemicals released from the seafloor. The deep ocean itself, though cold and dark beneath the ice, was not frozen. Warmed by geothermal heat from below, the water remained liquid, and its circulation patterns would have distributed heat and nutrients throughout the ocean basins. In this dark realm, microbial life that did not depend on sunlight could have survived. Bacteria and archaea capable of metabolizing chemicals from hydrothermal systems, or organisms that fed on the slow rain of organic matter from whatever photosynthetic life persisted near the surface. Some climate models suggest that in equatorial regions, a narrow band of relatively thin ice, perhaps only 2 to 10 meters thick, might have persisted where sublimation rates balanced freezing rates. Through such thin ice, enough sunlight could penetrate to support photosynthesis at rates sufficient for microbial survival. The transmissivity through 10 meters of clear ice exceeds 0.1% of surface light levels, which is adequate for certain photosynthetic organisms adapted to extremely low light conditions. Recent research analyzing modern Antarctic cryoconite ponds provides remarkable insights into how ancient life might have endured. Scientists studying meltwater ponds on Antarctica's McMurdo ice shelf discovered diverse eukaryotic communities thriving in these isolated pools. Each pond hosted a distinct assemblage of life: microalgae, protists, microscopic animals, with communities varying based on local conditions, particularly salinity. The diversity found in these modern analogues is striking. No two ponds were alike, yet all contained representatives from major eukaryotic groups, the complex cellular organisms that are ancestors of all animals, plants, and fungi. The microorganisms exhibited extraordinary physiological capabilities. Cultivated isolates from cryoconite holes in Antarctica, Greenland, and Svalbard could withstand extreme pH ranging from 2.5 to 10.5, salinities up to 10%, and some showed no decrease in viability even after 100 consecutive freeze-thaw cycles. These organisms could metabolize at least 58 different carbon sources, demonstrating remarkable metabolic flexibility. Both aerobic and anaerobic communities thrived, with anaerobic microorganisms showing particular success at temperatures near freezing, an adaptation that would have been crucial during Snowball Earth's long winters. Facultative anaerobes, organisms that can survive with or without oxygen, appear to be key players in these communities, able to reactivate after months of darkness and frozen conditions. The cyanobacteria living in these cryoconite ponds build small aggregates, biological structures that create localized microenvironments. These aggregates trap sediment and organic matter, darkening the ice surface locally and enhancing melting. Within the aggregates, both aerobic and anaerobic zones develop, supporting diverse microbial communities in close proximity. During Snowball Earth, similar biological aggregates could have created self-sustaining ecosystems on the ice surface, persisting for millions of years as isolated outposts of active life. The survival of photosynthetic eukaryotes, the ancestors of algae and plants, through Snowball Earth glaciations has been confirmed by biomarker evidence in rocks deposited after the deglaciation. These organisms must have found refugia that provided liquid water, sufficient light, and nutrients. The cryoconite pond hypothesis provides a plausible explanation for how such complex life forms endured conditions that would otherwise seem incompatible with their survival. The evidence suggests that life during Snowball Earth was reduced to small, isolated populations clinging to existence in scattered refugia. Genetic diversity would have declined significantly as populations became fragmented and many lineages went extinct, but some survived, and their descendants would eventually repopulate the planet when the ice melted. Life proved resilient, but barely. The glaciations pushed organisms to their physiological limits, testing every adaptation evolution had produced. The genetic consequences of surviving in such fragmented refugia would have been profound. Modern studies of Prochlorococcus, One of the most abundant photosynthetic bacteria in today's oceans reveal clear genetic signatures of population bottlenecks that occurred during the Neoproterozoic Snowball Earth events. The bacterial lineage experienced massive gene loss on the ancestral branch that existed during the Cryogenian period, between approximately 720 and 635 million years ago. This genome reduction event occurred precisely when the Sturtian and Marinoan glaciations were at their peak. The bottleneck left its mark in the DNA. Across genomic regions, researchers found an excess of deleterious mutations, genetic changes that would normally be removed by natural selection, but that accumulated because population sizes became so small that genetic drift overpowered selection. In tiny, isolated populations, harmful mutations can become fixed in the genome simply by chance, a phenomenon that leaves characteristic patterns in the DNA that persist for hundreds of millions of years. Temperature and light were the dominant stresses. Modern Prochlorococcus strains reach maximum growth rates at approximately 25 degrees Celsius and rarely survive when temperatures drop to around 10 degrees Celsius. During Snowball Earth, seawater temperatures beneath the ice plummeted to approximately 3.5 degrees Celsius, conditions that would have been lethal to most marine photosynthetic life. Combined with the exceedingly dim light penetrating through kilometers of ice, these conditions would have inhibited growth and proliferation dramatically. Yet adaptation occurred through these extreme conditions. Interestingly, most adaptive events during Snowball Earth happened through gene loss rather than gene gain. One notable exception was the duplication of a gene called PCBD, which encodes components of the photosynthetic antenna that captures light. This gene duplicated from 2 copies to 6 copies during the Snowball Earth period, boosting light harvesting capacity under the extremely low light conditions. After the glaciation ended and normal light levels returned, the extra copies became dispensable and were subsequently lost in some lineages. Fossil evidence confirms that diverse microbial communities existed immediately before, during, and after Snowball Earth glaciations. In the Death Valley region of California, researchers discovered diverse fossil microbiotas within glacial strata from the Neoproterozoic. The fossils include both prokaryotic organisms like cyanobacteria and eukaryotic microbes, more complex cells with nuclei. These fossils provide direct evidence that diverse life survived through at least one Snowball Earth event, challenging the notion that climatic perturbations catastrophically affected the entire marine biosphere. The microbial mats that formed in surface meltwater environments would have been complex ecosystems in miniature. Modern ice shelf meltwater lakes in the high Arctic and Antarctica host photosynthetic microbial mat communities dominated by filamentous cyanobacteria, but also containing diatoms, green algae, flagellates, ciliates, nematodes, tardigrades and rotifers. These consortia also harbour high concentrations of viruses and heterotrophic bacteria, up to 10 million to 100 million per square centimetre. During Snowball Earth, similar cryotolerant mats would have provided refugia for the survival, growth, and perhaps even the evolution of multicellular eukaryotes. The ocean beneath the ice, though isolated from the atmosphere, remained dynamically active. Models indicate that vigorous convective mixing kept the water column either uniform in the vertical direction or only weakly stratified. Compared to the modern ocean, the Snowball Earth ocean had far larger vertical mixing rates. This vigorous circulation, powered by geothermal heat from below, would have helped distribute nutrients and maintain conditions where chemosynthetic life could persist near hydrothermal vents. Life endured, but it paid a price. The long periods of isolation and extreme environments likely spurred genetic change, creating what scientists call bottleneck and flush cycles. Periods when populations crashed to small sizes, followed by expansions when conditions improved. These cycles may have accelerated evolutionary innovation, testing new adaptations in the crucible of survival. The world remained frozen, but beneath and upon the ice, life waited. You are beneath the ice now, far below the frozen surface, in a realm where Earth's interior heat still radiates upward through the crust. While the planet's surface remains locked in ice for millions of years, the processes deep within continue unperturbed by the frozen world above. Earth's interior does not care about the temperature at the surface. It remains hot, powered by the slow radioactive decay of uranium, thorium, and potassium that were incorporated into the planet when it formed more than 4.5 billion years ago. This heat must escape. It flows upward through the mantle by convection, hot rock rising, cooling rock sinking, in a cycle that operates over millions of years. Where this heat concentrates, where molten rock accumulates beneath weaknesses in the crust, volcanoes form. During Snowball Earth, these volcanoes continue to erupt, punching through the ice in isolated locations, sending plumes of ash and gas into the cold, dry atmosphere. Each eruption releases water vapor, sulfur dioxide, hydrogen sulfide, and, most importantly for Earth's future, carbon dioxide. Under normal circumstances, this volcanic carbon dioxide would be removed from the atmosphere within hundreds of thousands of years through a combination of processes. Rain would fall on exposed rock surfaces, and the slightly acidic water, made so by dissolving atmospheric carbon dioxide, would react with silicate minerals, consuming the gas in chemical weathering reactions. The dissolved products would wash into the ocean, where calcium and magnesium ions would combine with carbonate to form limestone that precipitates onto the seafloor. But Snowball Earth has disrupted this cycle almost completely. Most continental surfaces are buried beneath ice sheets. The atmosphere is cold and dry, holding very little water vapor. Precipitation falls sparingly, mostly as snow. Chemical weathering has slowed to a near standstill. The carbon dioxide released by volcanoes has nowhere to go. It simply accumulates in the atmosphere. This accumulation is the planet's escape mechanism, the slow unwinding of the frozen state. But it is extraordinarily slow, measured not in years or centuries but in millions of years. During the Sturtian glaciation, volcanic outgassing rates were at historic lows. The total length of mid-ocean ridges, the underwater volcanic, mountain chains where new oceanic crust forms and where much of Earth's volcanic carbon dioxide is released, reached a minimum during this period. Plate tectonic reconstructions show that between approximately 717 and 660 million years ago, the rate of seafloor spreading was unusually slow. This meant that less new oceanic crust was being created, and consequently, less volcanic gas was being released into the ocean and atmosphere. Estimates suggest that volcanic carbon dioxide output during the Sturtian was roughly half the rate that would occur during the early Phanerozoic, hundreds of millions of years later. This exceptionally low outgassing rate is likely the primary reason the Sturtian glaciation lasted so long, approximately 57 million years. The mathematics of accumulation are straightforward, but the timescales are immense. If volcanoes release carbon dioxide at a rate of, say, a few 100 million tons per year, a rate typical of modern volcanic activity, and if weathering removes almost none of it, then over 1 million years, substantial quantities will accumulate. But to build atmospheric carbon dioxide from near-present levels to concentrations hundreds of times higher requires tens of millions of years. When volcanic outgassing rates are low, the volcanoes erupt in darkness or in the pale light of the distant sun. Some break through the continental ice sheets, creating isolated volcanic islands of dark rock surrounded by white expanses. Others erupt beneath the sea ice, their heat melting through the frozen ocean surface, creating temporary openings that quickly refreeze. The lava flows across the ice or spreads across the seafloor, cooling and solidifying into basalt. Each volcanic plume adds a small increment to the atmospheric burden. The carbon dioxide molecules disperse into the cold atmosphere, where they remain indefinitely. Unlike today's atmosphere, where carbon dioxide cycles through the biosphere and hydrosphere in complex feedback loops, the Snowball Earth atmosphere offers no significant sinks. The gas simply accumulates year after year, millennium after millennium, epoch after epoch. The concentration rises slowly. From whatever levels existed when the ice first covered the planet, perhaps a few hundred parts per million, the carbon dioxide climbs toward 1,000 parts per million, then 10,000, then higher still. The increase is imperceptible on human timescales, but relentless on geological, untold climate models suggest that to break the grip of a hard snowball Earth, one where ice covers the entire planet, including the tropics, atmospheric, carbon dioxide must reach concentrations between 60,000 and 100,000 parts per million, or roughly 0.06 to 0.1 bar of pressure. Some models indicate even higher thresholds may be necessary, perhaps 0.2 to 0.4 bar, 200,000 to 400,000 parts per million, or roughly 200 to 400 times higher than modern pre-industrial levels. These estimates vary depending on the specific climate model used and the assumptions about cloud cover, atmospheric pressure effects, and other factors. The reason such extreme concentrations are required relates to the physics of infrared radiation and atmospheric absorption. Carbon dioxide absorbs infrared radiation, heat energy radiating from Earth's surface, at specific wavelengths. At low concentrations, each additional molecule of carbon dioxide contributes significantly to warming because the absorption bands are not yet saturated. But as concentrations rise, the strongest absorption wavelengths become saturated, meaning that adding more carbon dioxide produces diminishing returns in terms of additional warming. However, at very high concentrations, tens of thousands to hundreds of thousands of parts per million, other effects become important. Pressure broadening, where the increased atmospheric pressure causes carbon dioxide molecules to absorb infrared radiation across a broader range of wavelengths, enhances the greenhouse effect beyond what would be expected from the carbon dioxide concentration alone. Additionally, water vapor feedback becomes significant once temperatures begin to rise. Even slight warming allows the cold atmosphere to hold more water vapor, and water vapor is itself a powerful greenhouse gas, amplifying the initial carbon dioxide-driven warming. The volcanoes continue their work. Along mid-ocean ridges, magma wells up from the mantle, creating new oceanic crust and releasing dissolved carbon dioxide into the overlying water. Some of this gas dissolves in the ocean, but much of it eventually reaches the atmosphere. On continents and volcanic island arcs, subaerial volcanoes erupt directly into the air, sending their carbon dioxide skyward immediately. After 10 million years of glaciation, the atmospheric carbon dioxide concentration might reach 10,000 to 20,000 parts per million. After 20 million years, perhaps 20,000 to 40,000 parts per million. After 30 million years, approaching 40,000 to 60,000 parts per million. The progression is not linear. Volcanic activity varies, and the low outgassing rates during the Sturtian mean the accumulation proceeds more slowly than it would during other geological periods. But time is abundant, and the volcanoes are patient. For 57 million years, the Sturtian glaciation persists, the longest of the Neoproterozoic snowball events. During this immense span, carbon dioxide builds steadily, creeping toward the threshold that will finally break the planet free. The escape is inevitable, written into the planet's physics. As long as Earth's interior remains hot, as long as volcanoes continue to erupt, the frozen state cannot last forever. The timing is everything. During a more typical period in Earth's history, when mid-ocean ridges are more extensive and seafloor spreading rates are higher, volcanic outgassing could accumulate enough carbon dioxide to trigger deglaciation in perhaps 4 to 30 million years. But the Sturtian occurs during an anomalous low in tectonic activity. The rate of new oceanic crust formation along mid-ocean ridges is at a historic minimum. The volcanic carbon dioxide input rate is roughly half of what it will be during the Phanerozoic eon, which begins around 540 million years ago. This is why the Sturtian lasts so long, 57 million years from beginning to end. The low volcanic outgassing rate means carbon dioxide accumulates more slowly than it would during any comparable glaciation in Earth's later history. The planet remains frozen through epoch after epoch, waiting for the atmospheric burden to build to critical levels. Around 660 million years ago, after nearly 57 million years of accumulation, the threshold approaches. The exact concentration required depends on numerous factors: atmospheric pressure effects, cloud properties, the precise distribution of ice and dust on the surface. Different climate models yield different estimates, ranging from 0.06 bar to as high as 0.4 bar of carbon dioxide. This represents roughly 60,000 to 400,000 parts per million, between 150 and 1,000 times the pre-industrial atmospheric concentration of approximately 280 parts per million. The most sophisticated models, which account for pressure broadening of carbon dioxide absorption lines and the realistic behavior of clouds and atmospheric circulation, suggest a threshold around 0.2 to 0.3 bar may be most realistic for a hard snowball Earth. At these concentrations, the greenhouse effect becomes strong enough that even the highly reflective ice surface cannot maintain temperatures below freezing everywhere. The carbon dioxide continues its slow, inexorable rise. Volcanic eruptions add their increments. A few million tons here, a few million tons there. Each eruption is small compared to the vast reservoir accumulating in the atmosphere, but collectively, over millions of years, they tip the balance. The atmosphere grows denser as carbon dioxide accumulates. The increased pressure causes the carbon dioxide molecules to absorb infrared radiation across broader wavelength ranges than they would at lower pressures, an effect called pressure broadening. This enhances the greenhouse effect beyond what the carbon dioxide concentration alone would suggest. The planet's energy balance begins to shift. For tens of millions of years, the incoming solar energy and the outgoing infrared radiation have been nearly balanced at levels that maintain the frozen state. But now, with carbon dioxide approaching the critical threshold, the outgoing radiation decreases. More heat is trapped. Slowly, imperceptibly at first, temperatures begin to rise. The ice has held the planet for 57 million years. The volcanoes have worked patiently, building the key to freedom. The threshold is near. You are witnessing the moment when equilibrium breaks. Around 660 million years ago, after 57 million years of accumulation, atmospheric carbon dioxide reaches the critical threshold. The exact concentration remains uncertain. Perhaps 0.2 bar, roughly 200,000 parts per million, or 700 times the pre-industrial level. What matters is not the precise number, but the consequence. The planet's energy balance has shifted. For millions of years, incoming solar radiation and outgoing infrared radiation have maintained a frozen equilibrium. But now, with carbon dioxide at extreme concentrations, the greenhouse effect has grown strong enough to trap more heat than the ice can reflect. The global mean temperature, which has hovered around 50 degrees Celsius for tens of millions of years, begins to rise. The warming starts slowly, almost imperceptibly at first. Equatorial regions, where the sun delivers its most direct radiation even through the planet's high albedo, experience the earliest effects. During summer months, when the sun passes directly overhead, surface temperatures on the ice begin to climb above 20 degrees Celsius, then above 10 degrees. The ice does not melt immediately. Deglaciation will start when the annual mean equatorial surface temperature reaches approximately 7.7 degrees Celsius, not zero. At these temperatures, melt ponds begin forming on the ice surface. The process resembles what happens on modern sea ice during summer. Solar radiation warms the surface, creating shallow pools of liquid water. These ponds have much lower albedo than the surrounding ice, perhaps 0.2 compared to 0.6 or higher for snow and ice. The dark water absorbs far more sunlight than the ice reflects, warming further and expanding the melt area. This triggers the ice albedo feedback in reverse. More melting creates more dark water surface, which absorbs more sunlight, which drives more warming, which causes more melting. The same feedback that locked the planet into its frozen state now works to break it free. The process accelerates rapidly once initiated. Water vapor begins entering the atmosphere in quantities not seen for millions of years. The cold atmosphere, which has been extraordinarily dry throughout the glaciation, can now hold more moisture as temperatures rise. Water vapor is itself a powerful greenhouse gas, in some respects more potent than carbon dioxide. As atmospheric water vapor increases, it amplifies the warming initiated by carbon dioxide, creating another positive feedback loop. The equatorial ice begins to thin. Meltwater flows across the surface, pooling in depressions, darkening the ice with accumulated dust and sediment. Cracks appear as thermal stresses fracture the brittle ice. In places where the ice has thinned to just a few meters, enough sunlight penetrates to reach the liquid ocean beneath. The transition, once begun, proceeds with startling rapidity. Climate models and geological evidence suggest that the actual deglaciation, the period from initial melting to near-complete ice loss, occurs in just 2,000 to 10,000 years. This is merely a geological instant, a few millennia compared to the 57 million years the ice persisted. The planet lurches from one extreme to another, with the ice albedo feedback now working to amplify warming rather than cooling, and with extreme concentrations of carbon dioxide still filling the atmosphere. Temperatures soar. Earth transitions rapidly from an ice house into what scientists call a super greenhouse, a climate far warmer than anything that will exist in the modern world. The thaw has begun, and nothing can stop it now. Global mean temperatures climb from approximately 50 degrees Celsius to perhaps 30 degrees Celsius, or higher within just a few thousand years. Some estimates suggest temperatures could have reached as high as 48 to 50 degrees Celsius, hotter than anywhere on modern Earth. The exact peak temperature depends on how rapidly atmospheric carbon dioxide is removed through weathering and carbonate formation. But even the most conservative estimates indicate a global mean temperature of around 30 degrees Celsius when carbon dioxide concentrations remain at 15,000 parts per million. The hydrological cycle roars back to life with extraordinary intensity. For tens of millions of years, the atmosphere has been cold and dry, holding perhaps 1/10 the water vapor of modern times. Now, as temperatures soar and liquid ocean expands, evaporation accelerates dramatically. Water vapor pours into the atmosphere at rates Earth has never experienced before. The extreme temperature differences between the sun-heated tropics and the still cold polar regions drive powerful atmospheric circulation. Massive storm systems develop, what some researchers have termed hyperhurricanes, transporting enormous quantities of moisture from the warming oceans to the continents. These storms are far more intense than any modern hurricane because the temperature gradients driving them are so much steeper. Rain falls in torrents across landscapes that have not felt liquid water for millions of years. The precipitation is not gentle. It comes in sheets, driven by winds of extraordinary force. The carbon dioxide-rich atmosphere makes the rain acidic, creating what amounts to planet-wide acid rain that attacks exposed rock surfaces with unprecedented intensity. The melting ice itself creates massive freshwater input to the ocean. Roughly 1 kilometer of sea ice covering the entire planet, representing an immense volume of frozen fresh water, melts within a few thousand years. This fresh water, being less dense than salt water, initially forms a stratified layer on the ocean's surface, up to 2 kilometers deep in some reconstructions. The freshwater cap creates unusual conditions. The ocean becomes strongly stratified, with fresh water floating atop the saltier, denser water below. This stratification inhibits vertical mixing, creating a barrier between surface and deep ocean. Heat accumulates in the fresh surface layer, driving it to even higher temperatures. But this stratification does not last long. Ocean circulation, driven by wind stress and the density differences between the warming surface and cold deep water, begins breaking down the freshwater cap. Upwelling in high latitudes brings salty deep water to the surface. where it mixes with the freshwater layer. Within a few thousand years, a geological instant, the stratification breaks down and more typical ocean circulation patterns resume. The ocean warms throughout its depth, though this process takes longer than surface warming. Thermal expansion of the seawater causes sea level to rise by approximately 8 meters, with most of this occurring during the first 3,000 years after deglaciation. The warming ocean becomes a massive heat reservoir, moderating the wild temperature swings that characterize the early deglaciation period. The planet has escaped its frozen prison, but it now faces conditions almost as extreme at the opposite end of the temperature spectrum. The intense warmth and torrential rainfall trigger chemical weathering on a scale Earth has never witnessed. Fresh glacial sediment, ground to fine powder by millions of years of glacial grinding, covers vast areas of the continents. This glacial till is rich in reactive minerals, particularly calcium and magnesium silicates. When the acidic, carbon dioxide-rich rain falls upon this fresh material, weathering reactions proceed at extraordinary rates. The intensity of this post-glacial weathering is so extreme that geochemical evidence of it has been preserved in the rocks. Magnesium isotope ratios from sediments deposited at the end of the Marinone glaciation show a dramatic positive excursion, values reaching +0.56 to +0.95, indicative of the most intense chemical weathering episode recorded in these rocks. The lighter magnesium isotope is preferentially incorporated into weathering products, leaving the remaining dissolved magnesium enriched in the heavier isotope. The extreme enrichment signals that weathering was consuming rock at unprecedented rates. This weathering has crucial consequences for the atmosphere. The carbon dioxide that accumulated over tens of millions of years and triggered deglaciation now begins to be drawn down rapidly. Each reaction between carbon dioxide-rich rainwater and silicate minerals consumes atmospheric carbon dioxide, converting it into dissolved ions that wash into the ocean. The ocean receives massive inputs of weathering products, calcium, magnesium, bicarbonate ions, delivered by rivers swollen with meltwater and runoff. The alkalinity of seawater rises dramatically. Under normal circumstances, this alkalinity would be balanced by gradual carbonate precipitation. But the ocean is initially acidified by absorbing so much carbon dioxide from the atmosphere. Carbonate cannot precipitate until enough weathering-derived alkalinity accumulates to overcome the acidity. The delay is brief. Magnesium isotope data indicate that the climax of chemical weathering actually precedes the deposition of cap carbonates, the distinctive carbonate layers that mark the end of each snowball glaciation. Cap carbonate deposition did not occur until chemical weathering had consumed substantial quantities of atmospheric carbon dioxide and accumulated high levels of oceanic alkalinity. When carbonate precipitation finally begins, it does so explosively. The carbonate deposition rate rises rapidly in the first 10,000 years after deglaciation and reaches maximum values between 10,000 and 100,000 years after the ice melts. The calcium carbonate saturation state of seawater can reach values exceeding 70, far higher than the modern ocean, where values typically range from 3 to 5. Under such extreme supersaturation, carbonate minerals precipitate spontaneously from seawater. These cap carbonates form rapidly on a global scale. In the median model runs, depositing the estimated minimum global mass of cap carbonates takes between 32,000 and 591,000 years, with typical values around 127,000 to 162,000 years. This is geologically instantaneous, a layer of limestone accumulating worldwide in less time than modern humans have existed as a species. The carbonate precipitation locks away carbon dioxide that spent tens of millions of years accumulating in the atmosphere, only to remain for a few thousand years during the super greenhouse conditions, is now being permanently sequestered in limestone on the seafloor. The atmospheric concentration begins to decline rapidly. Within perhaps 100,000 to 200,000 years after deglaciation begins, Earth's climate starts stabilizing, the extreme greenhouse conditions moderate as carbon dioxide is drawn down, temperatures remain warm, far warmer than the frozen world that preceded, but no longer at the super greenhouse extremes of the immediate post-glacial period. The planet has completed its transition from icehouse to greenhouse. The thaw is nearly finished. You are standing on the floor of an ancient ocean, perhaps 10,000 years after the ice melted. The water around you, if you could be here, would be warm, far warmer than any modern tropical sea. The ocean has absorbed enormous quantities of heat from the super greenhouse atmosphere, and temperatures in the surface waters may reach 30 to 40 degrees Celsius or higher. But something more remarkable than temperature distinguishes this ocean from any that will exist in later epochs. The water is supersaturated, with dissolved calcium and carbonate ions to a degree that seems almost impossible. The saturation state, a measure of how much carbonate mineral the water can hold before spontaneous precipitation begins, exceeds 70 in some locations. In the modern ocean, saturation states typically range from 3 to 5, and values above 10 are considered extremely high. But this post-snowball ocean operates under conditions that have no modern parallel. The supersaturation results from the extraordinary weathering that followed deglaciation. Torrential rains fell on freshly ground glacial sediment rich in reactive minerals. Chemical weathering proceeded at rates perhaps 100 times faster than modern weathering. Rivers delivered massive quantities of calcium and magnesium ions to the ocean, along with bicarbonate ions derived from atmospheric carbon dioxide. The alkalinity of seawater rose to levels Earth had never experienced. For a brief period, perhaps a few thousand years, the ocean could not precipitate carbonates, despite this enormous influx of ions. The water was initially too acidic. Having absorbed vast quantities of carbon dioxide directly from the atmosphere during and after deglaciation, carbonate minerals dissolve in acidic conditions rather than precipitate. But as weathering continued to add alkalinity, the ocean's chemistry shifted. The pH rose, the acidity declined, and suddenly conditions favored carbonate precipitation on a massive scale. When precipitation begins, it happens explosively across the global ocean. Calcium carbonate crystals form spontaneously in the supersaturated water, growing rapidly and settling onto the seafloor. The crystals accumulate as layers of limestone, pure white rock composed almost entirely of calcium carbonate. In some locations, the carbonate that forms is dolomite, a magnesium-bearing carbonate mineral that rarely forms in modern oceans but appears common in cap carbonates. The deposition rate is extraordinary. In typical marine environments, carbonate sediments accumulate at rates measured in millimeters or centimeters per 1,000 years. But cap carbonate deposition proceeds at rates hundreds to thousands of times faster. Layers meters thick can accumulate in just tens of thousands of years. The rapidity leaves distinctive signatures in the rock. Large ripple marks cover the surfaces of many cap carbonate layers, undulating patterns created by strong currents moving across the seafloor. These ripples, preserved for more than 600 million years, indicate vigorous water movement during deposition. The ocean circulation in the immediate aftermath of deglaciation was intense, driven by extreme temperature, gradients, and the breakdown of the freshwater layer that initially formed from melting ice. Some cap carbonates display tubestone structures, cylindrical, formations that may represent escape routes for fluids or gases moving upward through the rapidly accumulating sediment. Others show evidence of seafloor cementation, where carbonate minerals precipitated directly onto the ocean floor, cementing sediment particles together almost instantaneously rather than requiring burial and compression. These features indicate conditions far from equilibrium, a system operating in overdrive. The cap carbonates form in stages. The first stage involves the most rapid precipitation, occurring within perhaps 10,000 years after deglaciation begins. During this phase, carbonate saturation states are at their peak, and precipitation rates reach maximum values. The limestone that forms is often relatively pure, composed primarily of calcium carbonate with few impurities. The second stage occurs as the freshwater layer begins mixing with the deeper ocean beneath. During glaciation, even beneath the ice, low-temperature seafloor weathering generated alkalinity in the deep ocean. This alkalinity remained trapped below the ice and after melting beneath the freshwater meltwater layer. When ocean circulation finally breaks down the stratification and mixes the meltwater with the alkaline deep water, a second pulse of carbonate precipitation occurs. This phase prolongs cap carbonate deposition, adding to the thickness of the accumulating layers. The third stage represents a gradual return toward normal marine conditions. Continental weathering continues, but at decreasing rates as the most reactive glacial sediments are consumed. Carbon dioxide levels in the atmosphere decline as carbonate precipitation locks away carbon. The ocean's chemistry slowly equilibrates, and precipitation rates decrease correspondingly. The total thickness of cap carbonates varies globally, but typically ranges from 3 to 30 meters, with a global average around 11 meters. Thicker deposits formed in low-latitude regions where alkalinity production and carbonate precipitation rates were highest. The entire accumulation, representing the transition from snowball conditions to more normal marine environments, was completed in roughly 30,000 to 600,000 years, with median estimates around 130,000 to 160,000 years. Perhaps the most distinctive chemical signature of cap carbonates is their carbon isotope composition. The carbonates are depleted in carbon-13, showing values between 3 and 5 per mil relative to the standard, strongly negative compared to typical marine carbonates, which usually have values near 0 or slightly positive. This negative signature appears in cap carbonates worldwide, providing a geochemical fingerprint that links these deposits to the extraordinary conditions following snowball deglaciation. The origin of this negative carbon isotope signature has been debated. Some researchers propose it reflects the destabilization of methane hydrates, ice-like structures that trap methane in seafloor sediments. When the planet warmed and pressure conditions changed, these hydrates could have released methane, which was then oxidized to carbon dioxide, containing mostly the lighter carbon-12 isotope. Others suggest the signature results from upwelling of deep ocean water that had accumulated isotopically light carbon during the glaciation, or from mixing of various carbon reservoirs in the ocean. Whatever the precise mechanism, the negative carbon isotope values distinguish cap carbonates from all other carbonate deposits in the geological record. Combined with their unusual sedimentary structures, their position directly above glacial deposits, their global distribution, and their distinctive geochemistry, cap carbonates serve as unmistakable markers of Snowball Earth events. The rocks preserve the memory of transformation, from a planet locked in ice to one awash in warm carbonate-saturated seas. The cap carbonates are Earth's record of its most dramatic climate reversal, written in limestone that will endure for hundreds of millions of years more. The cap carbonates become invaluable tools for stratigraphic correlation, matching rock layers across vast distances. Because they form rapidly and globally following each Snowball Earth event, they serve as time markers that allow geologists to synchronize rock sequences from different continents. The diamictite cap carbonate couplet, glacial deposits below, distinctive carbonates above, provides a unique signature that can be traced across the world. Different glaciation events produce cap carbonates with distinct characteristics. The Marinoan cap carbonates, deposited after the younger of the two major Neoproterozoic glaciations around 635 million years ago, show different lithologies and carbon isotope trends compared to Sturtian cap carbonates. Marinoan caps typically consist of laminated microcrystalline dolomites around 20 meters thick, with consistently negative carbon isotope values between 5.2 and 2.2 per mil. Sturtian cap carbonates, like the Tindalpina member in Australia, show different trends, often a decreasing carbon isotope signature, rather than the consistently negative values typical of Marinoan deposits. Some cap carbonates contain unusual phosphate-rich layers. These phosphorites, rocks rich in phosphorus minerals, formed when the post-glacial ocean became enriched in phosphorus released from weathering or from deep ocean reservoirs that accumulated during glaciation. The phosphate often appears in stromatolites, shrub-like structures, and coated grains associated with exposure surfaces on the cap dollostones. These phosphorus-rich deposits would have significant implications for life, as phosphorus is an essential nutrient that limits biological productivity in many marine environments. The shallow Neoproterozoic seas during cap carbonate deposition were likely phosphate-rich compared to modern oceans. Elevated phosphate concentrations may have strongly impacted the rate and tempo of carbonate mineral production, potentially explaining some of the unusual features observed in these rocks. The phosphorus enrichment would also have provided crucial nutrients for the microbial communities that survived the glaciation and the organisms that would subsequently evolve in the aftermath. Cap carbonates thus preserve not just a record of extreme climate change but also information about ocean chemistry, nutrient cycling, and the conditions that set the stage for evolutionary innovations. They mark boundaries in Earth history, the end of glacial epochs, and the beginning of warm, productive oceans. In many stratigraphic schemes, Marinoan-style cap carbonates mark the base of the Ediacaran period, which began around 635 million years ago, and witnessed the first appearance of complex animal life. The rocks remember the transition, preserving it layer by layer in limestone and dolomite that will endure until erosion or metamorphism finally destroys them. Each cap carbonate horizon tells the same story. Ice gave way to warmth, the ocean awoke from dormancy, and chemistry transformed in ways that would never be exactly repeated. The Sturtian glaciation has ended, its cap carbonate deposited, but Earth's experiments with extreme climate are not yet finished. You are standing in the aftermath of the Sturtian glaciation, roughly 660 million years ago. The cap carbonates have been deposited, the climate has stabilized, and Earth has returned to more moderate conditions. For millions of years, the planet enjoys relatively warm, stable climates. Life that survived the frozen world begins to diversify and expand. The ocean circulates freely, nutrients flow through marine ecosystems, and photosynthesis proceeds unimpeded beneath open skies. But the respite will not last. Around 650 million years ago, perhaps 10 million years after the Sturtian ended, Earth's climate begins cooling once more. The same conditions that triggered the first snowball glaciation remain present in Earth's system. Continental fragments still occupy low latitudes where weathering rates remain high. The sun is still 6% dimmer than it will be in the modern era. The planet's climate system remains sensitive to perturbations in carbon dioxide levels and other greenhouse gases. The trigger this time may be different from what initiated the Sturtian. Some evidence suggests massive volcanic eruptions, large igneous provinces that release both aerosols and carbon dioxide, may have played a role. Volcanic aerosols can cool the planet by reflecting sunlight, while the subsequent weathering of fresh volcanic rock consumes atmospheric carbon dioxide over longer timescales. Other factors may have contributed: changes in ocean circulation, variations in Earth's orbital parameters, or continued drawdown of atmospheric carbon dioxide through silicate weathering. Whatever the precise mechanism, ice begins forming at high latitudes once more. Glaciers advance from polar regions. Sea ice expands across the ocean surface. The ice albedo feedback, dormant for millions of years, awakens again and begins driving the planet toward another frozen state. Around 645 million years ago, the Marinoan glaciation begins in earnest. Named for the Merino Formation in South Australia where it was first identified, this second Snowball Earth event follows the same physical processes as the Sturtian, but unfolds under slightly different conditions. The Marinoan will be shorter than its predecessor, lasting perhaps 4 to 15 million years rather than 57 million, but it will be equally severe. Ice once again advances toward the equator. The familiar cascade of feedback loops takes hold. Cooling leads to more ice. More ice reflects more sunlight. Reflected sunlight drives further cooling. Continental weathering slows as ice covers the land. Carbon dioxide begins accumulating in the atmosphere from volcanic outgassing. The planet descends into another deep freeze. By approximately 635 million years ago, the date marked by the distinctive Marinoan cap carbonates found worldwide, Earth has been frozen for millions of years. Global mean temperatures have plummeted to levels comparable to the Sturtian. The ocean is sealed beneath ice up to a kilometer thick. Life persists in scattered refugia, clinging to existence in meltwater ponds, near hydrothermal vents, or beneath thin ice, where light can still penetrate. The Marinoan glaciation demonstrates that Snowball Earth was not a single anomalous event, but a recurring phenomenon during this era of Earth's history. The planet's climate system during the Neoproterozoic was poised on a knife's edge, capable of tipping into runaway glaciation when conditions aligned. The fact that Earth froze twice within roughly 80 million years reveals something profound about climate sensitivity and the feedback mechanisms that govern planetary temperatures. The second freeze will end the same, way the first did, through the patient accumulation of volcanic carbon dioxide over millions of years until greenhouse warming becomes strong enough to break the ice's grip. Around 635 million years ago, the Marinoan deglaciation begins. Within a few thousand years, the ice melts, the planet lurches once more into super greenhouse conditions. Torrential rains fall, intense weathering strips carbon dioxide from the atmosphere, and cap carbonates precipitate rapidly on the seafloor. But this time, something different will follow the thaw. The Marinoan cap carbonates that mark the end of this glaciation are among the most distinctive in the geological record. They consist primarily of laminated microcrystalline dolomites, typically around 20 meters thick, with carbon isotope values that remain consistently negative, between 5.2 and 2.2 per mil throughout their thickness. This differs from Sturtian cap carbonates, which often show an upward trend from negative to positive carbon isotope values. The Marinoan caps formed rapidly, possibly within 30,000 to 600,000 years. The three-stage process of formation, driven first by rapid continental weathering, then by mixing of meltwater with alkaline deep ocean water, and finally by gradual return to equilibrium conditions, left distinctive geochemical signatures. Phosphate-rich layers in some locations indicate nutrient-rich conditions in the post-glacial ocean. What makes the Marinoan glaciation particularly significant is not just its severity, but its timing. The end of the Marinoan, marked by its distinctive cap carbonates, defines the base of the Ediacaran period, the final period of the Proterozoic eon. The Ediacaran would witness remarkable developments in the history of life, developments that may have been influenced or even triggered by the extreme environmental conditions of Snowball Earth. After the Marinoan deglaciation, Earth's climate stabilized in ways it had not during the interval between the Sturtian and Marinoan glaciations. No more Snowball Earth events would occur. The planet entered a new phase in its history, one characterized by more moderate climates and, crucially, by the appearance of complex multicellular life. The reasons Earth did not freeze again remain a subject of scientific investigation. Perhaps continental configurations changed, reducing the efficiency of silicate weathering at low latitudes. Perhaps volcanic outgassing rates increased as plate tectonics accelerated. Perhaps rising atmospheric oxygen levels, which continued to increase during the Ediacaran, helped stabilize the climate through complex feedbacks involving methane and other greenhouse gases. Or perhaps life itself, diversifying rapidly after the Marinoan thaw, began exerting stronger influences on atmospheric composition and climate regulation. Whatever the reasons, the era of Snowball Earth had ended. Earth had tested the limits of planetary habitability twice, and emerged both times with life intact, battered but resilient. The frozen worlds that seemed as though they might last forever had proven temporary, undone by the patient work of volcanoes that never stopped releasing carbon dioxide, even when the surface was locked in ice for millions of years, the Marinoan glaciation concluded around 635 million years ago. The ice melted, the ocean awoke, and cap carbonates precipitated across the globe. Earth would never again experience conditions quite so extreme. But the legacy of Snowball Earth was only beginning to unfold. You are witnessing the Ediacaran period, the time immediately following the Marinoan glaciation, beginning around 635 million years ago. The ocean has recovered from its frozen state. Temperatures have moderated after the initial super-greenhouse conditions. Nutrients released by intense post-glacial weathering circulate through marine ecosystems, and something extraordinary is about to happen, or perhaps has already begun, during the final stages of deglaciation. Complex multicellular life begins to appear in the fossil record in ways it never had before. The connection between Snowball Earth and the subsequent diversification of life has captivated scientists for decades. Did the extreme environmental stresses drive evolutionary innovation? Did the nutrient pulses from intense weathering provide resources for larger organisms? Did the population bottlenecks force organisms through genetic crises that accelerated change? The evidence suggests all these factors played roles. The genetic signatures preserved in modern organisms, particularly the gene losses and adaptations found in ancient bacterial lineages, indicate that Snowball Earth events created severe bottlenecks that reshaped the tree of life. Organisms that survived were those capable of extraordinary physiological flexibility, able to withstand freeze-thaw cycles, capable of metabolizing under extreme conditions, adapted to low light and scarce nutrients. When conditions improved after the Marinoan thaw, these survivors found themselves in an ocean enriched with phosphorus and other nutrients released by weathering. The phosphate-rich cap carbonates indicate elevated nutrient levels that would have supported increased biological productivity. Oxygen levels in the atmosphere were rising, reaching concentrations that could support larger organisms with higher metabolic demands. The Ediacaran biota, strange, often flat, leaf-like organisms unlike anything alive today, appeared in the fossil record. Some resembled quilted mattresses, others looked like fronds anchored to the seafloor. Still others were disc-shaped or branching. They were not like modern animals in most respects, but they represented a crucial step toward complexity. Multicellular organisms large enough to leave visible fossils, diverse enough to occupy multiple ecological niches. By the end of the Ediacaran, around 539 million years ago, even more complex organisms appeared. Creatures with bilateral symmetry, with evidence of burrowing behavior, with the beginnings of the body plans that would explode into diversity during the Cambrian period. The Snowball Earth events had set the stage, creating conditions that tested life to its limits and then, in their aftermath, provided opportunities for innovation that had never existed before. The harsh snowball conditions may have driven early organisms to develop colonial strategies for survival, single cells aggregating together for protection and resource sharing. The repeated freeze-thaw cycles could have provided selective pressure favoring organisms that could coordinate their activities, share metabolic products, and eventually differentiate into specialized cell types. The post-glacial nutrient pulses rewarded larger body sizes that could capture and process more resources. Scientists continue to debate the precise mechanisms linking Snowball Earth to the rise of complex life. Some argue the connection is direct, that extreme stress accelerated evolutionary innovation. Others suggest the link is indirect, that Snowball Earth altered ocean chemistry and nutrient cycles in ways that subsequently favored complexity. Still others propose that the timing is coincidental, that life was already on a trajectory toward complexity and the glaciations merely interrupted, but did not fundamentally alter that path. What seems clear is that after hundreds of millions of years dominated by single-celled organisms and simple microbial communities, the Ediacaran and Cambrian periods witnessed an explosion of innovation. Within roughly 100 million years after the Marinoan glaciation ended, the ocean contained representatives of virtually all major animal groups that exist today. Arthropods, mollusks, echinoderms, chordates, and many others. The frozen world had given way to one teeming with diverse, complex life. Earth had emerged from its most extreme climate test not diminished, but transformed, carrying life forward into new realms of possibility. You return now to the present, to a world that bears only subtle traces of its frozen past. More than 635 million years have passed since the last Snowball Earth event ended. The continents have drifted across the globe multiple times, assembling into supercontinents and fragmenting again. The ocean has been filled and refilled countless times. Mountains have risen and eroded away. Life has diversified into millions of species, colonizing every habitat from the deepest ocean trenches to the highest mountaintops. Yet the memory of Snowball Earth remains, written in rocks scattered across every continent. In the Flinders Ranges of South Australia, glacial deposits from the Sturtian period lie exposed, testifying to ice that once covered tropical latitudes. On Pikes Peak in Colorado, ancient rocks contain evidence of low-latitude glaciation. In Scotland and Ireland, the Port Ascaig Formation preserves rare records of the frozen world. In China, in Namibia, in Svalbard, everywhere geologists look, they find the distinctive couplet of glacial diamictites overlain by cap carbonates. These rocks tell a story that stretches the imagination. They speak of a planet pushed to climatic extremes beyond anything humans have witnessed. They reveal feedback mechanisms that can drive Earth from moderate conditions to complete ice coverage in perhaps just thousands of years. They demonstrate that the planet's climate system has tipping points beyond which change accelerates uncontrollably. The lessons of Snowball Earth resonate today. Modern Earth faces its own climate crisis, driven by human activities that have increased atmospheric carbon dioxide to levels not seen for millions of years. While current warming does not approach snowball conditions, the underlying principles remain the same. Feedbacks can amplify change. Tipping points exist where systems transition rapidly between states, and once certain thresholds are crossed, returning to previous conditions becomes extraordinarily difficult. Snowball Earth shows us that ice albedo feedback can work in both directions, amplifying cooling until the planet freezes, or amplifying warming once deglaciation begins. It demonstrates that carbon dioxide accumulation over millions of years can eventually overcome even the highest planetary albedo. It reveals that weathering acts as Earth's thermostat, but one that operates on geological timescales, too slow to prevent extreme excursions when other factors align. Perhaps most importantly, Snowball Earth teaches us about resilience. Life survived conditions that seemed incompatible with its existence. Microorganisms found refugia in meltwater ponds, beneath thin ice, near hydrothermal vents. They endured tens of millions of years in isolation, maintaining genetic diversity through repeated bottlenecks. When conditions improved, they repopulated the planet and diversified in ways that eventually led to all complex life, including humans. The rocks remember. Paleomagnetic signatures locked into glacial deposits preserve the latitudes at which ice formed. Carbon isotopes and cap carbonates record the chemistry of post-glacial oceans. Uranium lead dates in zircon crystals mark the precise timing of volcanic eruptions that punctuated the frozen epochs. Striated bedrock surfaces show the direction ice flowed. Dropstones in marine sediments prove that icebergs floated in tropical seas. These are not abstract reconstructions or speculative scenarios. They are physical evidence, as solid as the ground beneath our feet. The stones speak with certainty. Earth was frozen from pole to pole, not once but twice, for millions of years each time. The planet survived, life survived, and in the aftermath, complexity emerged. As you reflect on this ancient story, consider the timescales involved. The Sturtian glaciation lasted 57 million years, longer than the entire Cenozoic era that has elapsed since the extinction of the dinosaurs. The volcanic accumulation of carbon dioxide that eventually triggered deglaciation required patience, measured not in human lifetimes or civilizational timescales, but in millions of years of continuous outgassing. The processes that govern planetary climate operate on scales that dwarf human perception. Yet Earth's climate can also change rapidly when feedback aligns. The transition from snowball to super greenhouse occurred in mere thousands of years, a geological instant. Ice that had persisted for millions of years melted away in a time span comparable to recorded human history. This demonstrates that while some Earth system processes operate slowly, others can accelerate dramatically once critical thresholds are exceeded. The echoes of Snowball Earth reach forward through time in the diversity of life that surrounds us. Every animal, every plant, every fungus descends from organisms that survived those frozen epochs. The genetic adaptations forged during survival in extreme conditions persist in DNA sequences we can read today. The evolutionary innovations driven by environmental stress still shape the capabilities of living things. When you touch a rock containing glacial scratches from 650 million years ago, you connect directly with that ancient world. The stone has endured, preserving its message across an expanse of time so vast that human history represents less than 1/100th of 1% of it. The rock asks you to imagine ice covering everything, temperatures colder than Antarctica, darkness beneath frozen seas, and still, somehow, life persisting, waiting for the world to thaw. Snowball Earth is not a cautionary tale about climate change, though it offers lessons. It is not primarily a story about life's resilience, though that emerges clearly. It is, most fundamentally, a demonstration of Earth as a dynamic system, capable of extraordinary transformations, governed by physical laws that operate regardless of what exists on its surface, yet responsive to changes in atmosphere, ocean, and biosphere in ways that can amplify small perturbations into global catastrophes or recoveries. The frozen world is gone. The ice has melted, the oceans flow freely. Life has diversified beyond anything that existed before the glaciations. But the evidence remains, etched in stone, waiting to be read by those who know how to interpret its language. This is the end of your journey through Earth's deepest freeze. The story it tells is one of extremes, of survival against improbable odds, of a planet that has tested the boundaries of habitability and emerged transformed. The rocks remember everything, and now so do you. Yet the memory of Snowball Earth remains, written in rocks scattered across every continent. In the Flinders Ranges of South Australia, glacial deposits from the Sturtian period lie exposed, testifying to ice that once covered tropical latitudes. On Pikes Peak in Colorado, ancient rocks contain evidence of low-latitude glaciation. In Scotland and Ireland, the Port Ascaig Formation preserves rare records of the frozen world. In China, in Namibia, in Svalbard, everywhere geologists look, they find the distinctive couplet of glacial diamictites overlain by cap carbonates. These rocks tell a story that stretches the imagination. They speak of a planet pushed to climatic extremes beyond anything humans have witnessed. They reveal feedback mechanisms that can drive Earth from moderate conditions to complete ice coverage in perhaps just thousands of years. They demonstrate that the planet's climate system has tipping points beyond which change accelerates uncontrollably. The lessons of Snowball Earth resonate today. Modern Earth faces its own climate crisis, driven by human activities that have increased atmospheric carbon dioxide to levels not seen for millions of years. While current warming does not approach snowball conditions, the underlying principles remain the same. Feedbacks can amplify change. Tipping points exist where systems transition rapidly between states, and once certain thresholds are crossed, returning to previous conditions becomes extraordinarily difficult. Snowball Earth shows us that ice albedo feedback can work in both directions, amplifying cooling until the planet freezes, or amplifying warming once deglaciation begins. It demonstrates that carbon dioxide accumulation over millions of years can eventually overcome even the highest planetary albedo. It reveals that weathering acts as Earth's thermostat, but one that operates on geological timescales, too slow to prevent extreme excursions when other factors align. Perhaps most importantly, Snowball Earth teaches us about resilience. Life survived conditions that seemed incompatible with its existence. Microorganisms found refugia in meltwater ponds, beneath thin ice, near hydrothermal vents. They endured tens of millions of years in isolation, maintaining genetic diversity through repeated bottlenecks. When conditions improved, they repopulated the planet and diversified in ways that eventually led to all complex life, including humans. The rocks remember. Paleomagnetic signatures locked into glacial deposits preserve the latitudes at which ice formed. Carbon isotopes and cap carbonates record the chemistry of post-glacial oceans. Uranium lead dates in zircon crystals mark the precise timing of volcanic eruptions that punctuated the frozen epochs. Striated bedrock surfaces show the direction ice flowed. Dropstones in marine sediments prove that icebergs floated in tropical seas. These are not abstract reconstructions or speculative scenarios. They are physical evidence, as solid as the ground beneath our feet. The stones speak with certainty. Earth was frozen from pole to pole, not once but twice, for millions of years each time. The planet survived, life survived, and in the aftermath, complexity emerged. As you reflect on this ancient story, consider the timescales involved. The Sturtian glaciation lasted 57 million years, longer than the entire Cenozoic era that has elapsed since the extinction of the dinosaurs. The volcanic accumulation of carbon dioxide that eventually triggered deglaciation required patience, measured not in human lifetimes or civilizational timescales, but in millions of years of continuous outgassing. The processes that govern planetary climate operate on scales that dwarf human perception. Yet Earth's climate can also change rapidly when feedback aligns. The transition from snowball to super greenhouse occurred in mere thousands of years, a geological instant. Ice that had persisted for millions of years melted away in a time span comparable to recorded human history. This demonstrates that while some Earth system processes operate slowly, others can accelerate dramatically once critical thresholds are exceeded. The echoes of Snowball Earth reach forward through time in the diversity of life that surrounds us. Every animal, every plant, every fungus descends from organisms that survived those frozen epochs. The genetic adaptations forged during survival in extreme conditions persist in DNA sequences we can read today. The evolutionary innovations driven by environmental stress still shape the capabilities of living things. When you touch a rock containing glacial scratches from 650 million years ago, you connect directly with that ancient world. The stone has endured, preserving its message across an expanse of time so vast that human history represents less than 1/100th of 1% of it. The rock asks you to imagine ice covering everything, temperatures colder than Antarctica, darkness beneath frozen seas, and still, somehow, life persisting, waiting for the world to thaw. Snowball Earth is not a cautionary tale about climate change, though it offers lessons. It is not primarily a story about life's resilience, though that emerges clearly. It is, most fundamentally, a demonstration of Earth as a dynamic system, capable of extraordinary transformations, governed by physical laws that operate regardless of what exists on its surface, yet responsive to changes in atmosphere, ocean, and biosphere in ways that can amplify small perturbations into global catastrophes or recoveries. The frozen world is gone. The ice has melted, the oceans flow freely. Life has diversified beyond anything that existed before the glaciations. But the evidence remains, etched in stone, waiting to be read by those who know how to interpret its language. This is the end of your journey through Earth's deepest freeze. The story it tells is one of extremes, of survival against improbable odds, of a planet that has tested the boundaries of habitability and emerged transformed. The rocks remember everything, and now so do you.